talk about explainable AI. So explainable AI is itself a vast topic. It's not possible to cover it in the short span of time. So my plan for today is to give an overview of the explainability framework, existing methodologies, some interesting work that has recently come out, and also the existing IR and NLP explainable algorithms. Explain some of the IR and NLP explainability algorithms and align it with the existing methodologies. So this is the overview of my work. First, I will talk about the explainability framework. Then I will talk about the methodologies used for explainability in general. And then I will talk about the evaluation methodologies used for explainability. And then at the end, I will talk about some interesting works in explainability and some future directions. So what is explainable AI? So it's a framework which helps to interpret the decisions or predictions made by an AI model, which can be a machine learning model or can be a deep learning model. And the target audience for this interpretation can be a layman or a stakeholder or people having domain expertise. The motivation for explainability is to build socially responsible and trustworthy AI models. So here I'm showing an example use case scenario for explainability. So this is a explainable model for an information retrieval model. So what happens in an information retrieval model? You give a query and it shows you a ranked list of documents. So now here the target audience for explainability is the common people who do not have any kind of IR expertise. So what a layperson can understand. So here you can see that the explainability model is showing some words or phrases given the query and document pair as input to the model. So what the layperson can understand from that these particular words or maybe because of these particular words or phrases, the document has been ranked to a particular position by the retrieval model. And if this kind of highlights, these words or phrase highlights, correlates with the user's intuition, then user will have more trust in the retrieval model. So that's how it happens. This is another use case scenario where the target audience are doctors who have the domain expertise. So suppose we have a model which explains that where given a patient's condition, it predicts whether the disease is infectious or not. So there, the explainer can explain that what are the top K features, for example, headache or sneezing, or this kind of features, based on which the model has decided that the person has an infectious disease or not. And since the doctor has a domain expertise, they can verify if they give green signal that the model is kind of giving importance to the features where it actually should give more importance. Then we can understand that the predictive model is working well. This is another example scenario where the target audience are stakeholders. So who are the stakeholders that deploy a model? So their interest is in, like, if the model performs well, then they will get benefited from that. So this is a model in law domain. So suppose where the case details are given and the model predicts the charge to which the particular case has to be assigned. Now the explainer can explain that what are the features, for example, the crime evidence or the nature of the crime, based on which the model has tagged that particular case to a particular charge. And then if the stakeholder checks that the features that the model is using is not right, then it can take a recourse and change the particular prediction of the model. So that's why this is another example where the target audience are the stakeholders. So what is the motivation for explainability? So we can verify a lot of different things using the explainable framework. So the first one is the model following a non-expert intuition? As I have shown in the first use case, that we were showing the IR model explanations to a lay person. So if that particular model follows the intuition of a common person, then that particular person will have more trust in the model. So that is one benefit. Another is the model following the expert intuition, which is required for the like where the AI models are used in the sensitive areas like healthcare domain and all these kind of things. It also helps the stakeholder, as I have already explained, that if the stakeholder has confidence in the model, he will be eager to invest in the process. And we can also develop trustworthy model through reports. So if explanations are not trustworthy, then the algorithm can take reports and modify them and modify itself. So in that way, it also helps to develop trustworthy models. Another important aspect of explainability is that it also helps to check, is the model fair? So fairness is an important topic in today's world. The predictions made by an AI model should be fair in terms of gender, race, or any other socially sensitive attributes. So explainability can help us to understand that whether the model is fair with respect to these attributes or not. Suppose we get explanations that this particular model is giving more importance to gender or race for the particular prediction, then we can understand that the model is not fair. So that's how fairness.
Just sorry to interrupt. So this is like when you mean a bias, it means the accuracy is more for certain gender compared to others. Is it something like that?
Yes, but like by explainability here, accuracy doesn't matter. Here, yeah. What I'm saying is like suppose the model has predicted something, and the explainable model shows that it has put highest importance on the gender of that particular person. Yeah, so that can be verified, and then we can say that the model is biased. So here I'm trying to explain the research trajectory about the explainability research. Here I have classified it into 3 different regions, so 2016 to 2019, which was the very initial stage of explainability, where people are trying different kind of device-defined kind of post-hoc explanations. Where people are building different kind of explainers for complex models. So it's not that people are not researching on these kind of things anymore, but like that was the first step when a lot of people are trying these kind of things. Then from 2018 to 2022, it took a change where people are examining the state-of-the-art explainer models, that are explainable approaches trustworthy? Can we trust this particular explanation or not? And then from 2022, it was a new way forward where we're changing, can we change the notion of explainability? So how we can build more interactive and useful explanations for the user. So these are the kind of new dimensions that has been added over the course of time in the explainability research. So I am like for today's talk, I will mainly focus on the first part, that 2016 to 2019. But at the end of the talk, I will try to touch some of the this critical examination part and the finding new ways forward thing. So what should be the properties of an explanation model? So this concept of explainability is both important and slippery. So this Lipton's work has a very detailed description of how the explanation should be. But here I have tried to jot down the important points. So like it should provide transparency to the model. So regarding transparency, there can be 2 different aspects. One is decomposability. So where each part of the model admits an intuitive explanation. So one example is like suppose in like for image classification explanations, people have tried to explain that what is the meaning of different layers of the deep neural network. So this kind of decomposability should be one of the properties of a good explainer model. And they should have the simulatability. If a person can contemplate the entire model at once, that should also be one of the properties of a good explainer. It should have the post hoc interpretability. So it should present a distinct approach to extracting information from the learned models. And they often do not elucidate precisely how a model works. They may nonetheless confer useful information for practitioners and end users of machine learning. So yeah, these are the properties. So here I am showing that there in certain settings, there may exist a trade-off between explainability and accuracy. As you can see here, like from linear regression, decision trees, random forest, and neural networks. So decision trees, random forest, their models are kind of inherently explainable, but the accuracy may hamper for complex problems. So, but neural networks has higher accuracy, but the interpretability is less. So this kind of trade-off exists in certain settings. So what are the approaches towards explainability? So there are two, like broadly, we can categorize into two different areas. One is the explaining without a separate explainer model and explaining with a separate explainer model. So in the first category, the model takes as input human interpretable features, and the working principle of the model is inherently interpretable. An example is decision tree. And for the second part, so these kind of explainers are necessary for complex models, obviously, and also for the models where we do not have access to the model architecture, like we have access only to the black box model. Then in those scenarios, we use this kind of explainer. What this explainer does is it tries to mimic the prediction of the original model. And obviously with a much simpler architecture compared to the original model. So that's the kind of way. So this is the example of a inherent explanation example with decision trees. So here you can see in this diagram that the decision tree is trying to predict whether a person is fit or not. And the kind of different features it uses is age, eats a lot of pizza, exercise in the morning. So suppose the input comes, we know that if the person has less than 30 age, then it will follow the left-hand side path, which is eats a lot of pizza. And then based on yes or no, the model will predict that whether the person is fit or unfit. Similar thing happens for like if the age is greater than 30, then it will check whether the person exercises in the morning or not. Based on yes or no, it will predict fit and unfit. So the different hierarchical condition it checks is clearly transparent, and we can understand that how the model is working. That's why we are saying that it's an inherently explainable model.
Sorry to interrupt. So what is the difference between transparency and inherently interpretable or explainable model?
Inherently interpretable models have the transparency property, obviously.
Yeah, so what is the difference between?
It's not different. That's the property and this is the category. I'm saying that explainability framework, like the algorithms that has been developed, like they can be categorized into two areas where, like the first one where we are using the, the inherently explainable models, and the other one where we are using separate explainable. That is the categorized.
All the properties guaranteed.
Yeah, first one obviously have the other. This is one inherent expansion example in IR. So in this work, this is a 2013 work. Obviously, the work was not done without thinking of the explainability. So they trained a SVM network. So the model here, what it does is that given a pair of queries, it predicts that whether that belong to a particular search task or not. I mean, if the similarity is greater than a particular threshold, then it predicts that the pair of queries belong to a particular search task. So by search task, I mean that it's a set of queries where people are generally engaged in a particular topic. They are similar. They are related to a particular semantical topic or something. So so they trained a SVM model, and the model was predicting the similarity between the pair of queries, and then there was a threshold. Based on that, they tried to cluster the set of queries. So the SVM takes the features like URL similarity, click behavior, n-gram similarity between a pair of queries, and the trained SVM model has the weights for each of these features. So based on that, that's why I'm saying that the model is inherently explainable, because we know that given a pair of queries, what are the important features? The trained SVM has that weights for each features, and that will give us a transparency. Okay, so the model is giving this much importance to this particular feature, and then based on that, it is giving us the level for a particular pair of queries. So this explaining with a separate explainer is also known as post hoc explanations. And as I have already explained that sometimes we do not have also access to the actual model. We only have the access to the black box model. In those scenarios, these kind of explainers are very useful. And but given like this kind of algorithms, but still an inherently interpretable model is always preferable. So there has been like two similar terms in the literature, which is like explainability and interpretability. To be honest, there is no kind of formal definition of interpretability. According to certain studies, when the working principle of the model is explainable, it is interpretable. So essentially, we can say that inherently explainable models are known as interpretable models. But this is just the terminology that I wanted to explain, that these terminologies are related. So now we'll talk about types of post hoc explanations. So by post hoc explanations, obviously I mean the explainers, like where we have a separate explainer model along with the original model. So we can broadly categorize these post hoc explanations into two areas, which are local explanation and global explanation. So in local explanation, it takes a particular neighborhood around a sample point, as you can see in this diagram. So this is the decision boundary. Like the curved line is the decision boundary of the model. So if you focus on a particular region, so it takes that point and tries to fit a explainer based on that region. That's why it's called local explanation. It is more likely to give better explanations for complex boundary. As I already explained, that our inherent tendency should be to train an explainer which is much simpler than the original model. So if we focus on a particular region, maybe we can fit for a complex model. If we focus on a particular local neighborhood, maybe we can fit a simpler model over there. So that's why this local explanation thing came out. And the another one is this global explanation, which may be difficult, obviously, for complex models, but it gives an overview of the whole model. So this is a comparison of local versus global. So local explains individual predictions, whereas the global explains the complete behavior of the model. The local explanation helps unearth the biases in the local neighborhood of a given instance, and whereas global explanation helps shed light on the big picture biases affecting the larger subgroup. Local explanation helps vet if the individual predictions are being made for the right reasons, whereas global explanations help vet if the model at high level is suitable for deployment. So these are some points. So here is an example of local explanation in NLP. So this is also another one. Also, this paper came out. When this paper came out, then there was not this so-called explainability concept, because it came out in 2016. So in this works, they propose a joint model that a model that jointly learns to align and translate. It's a machine translation model. So this aligned model estimates how well the input around position J matches with the output at position I. So the alpha I, which is the output of this alignment model, are the local explanations. So as you can see in this matrix, so like in one row we are showing the English translation, and the other there is this French translation, the French sentence. And now it's trying to the heat map in this matrix is showing the importance of all the different words in translating for a particular token in the input sentence. So this is one good example of local explanation in NLP. So now we'll talk about the approaches used for local explanations. So the different approaches are feature importance estimation, rule-based, saliency maps, prototypes or example-based, and counterfactual examples. I will go by each of these things now. So what is this feature importance? So here we train an explainer model, for example, regression model based on human interpretable input, sorry for the typo, and the model predicted output. The explainer will estimate the importance of different human interpretable features. It is mostly model agnostic. It doesn't depend on the model architecture. So one of the most famous feature importance based explainer is LINE. It came out in 2016. So it provides sparse linear local explanations. So what it does, it takes epsilon neighborhood around each point, each data point, and train a classifier for those points. The classifier estimates the importance of different features. And while training this classifier, like each point is weighted by the distance. I mean, like here we have a distance function based on which we take this epsilon neighborhood. So each point, the training point is weighted by this, inversely weighted by this distance function. So I mean, like the diagram that I showed for local explanation. So what it does is that for this circular region, suppose it tries to fit a linear regression model over there. So, and that's how it tries to explain that region, the predictions in that region. I have just pasted the algorithm, the step-by-step algorithm for line over here, but it essentially does the same thing what I said now. So Lime has also a global explanation algorithm, which is I mean, like, which is constructed from the local explanations. So in the global explanation, what it does is, like, for each sample point, it first creates the local explanations, and then, as you can see in this the right-hand side diagram, so it forms this kind of matrix. So we have, suppose, these 5 different features and all the sample points, and then for each feature, we average the contribution for all the sample points. Then we try to take those set of features which can which will give us the maximum coverage. So that's how we say that, like, suppose for this picture we can say that F2, F3, and F4 and F5 gives us the maximum coverage. The combination of this F2, F3, F4, F5 gives the maximum coverage. So that's kind of give us the global explanation about the model. So yeah, that's the global explanation using Lime. So this is an example of Lime application in an NLP task. So here the classifier predicts whether a particular document is about Christianity or atheism. And as you can see that in this diagram, it is showing that there are 2 algorithms, and it is showing the importance of different words that the importance of different words in these 2 algorithms. And yeah, so for the first algorithm, it predicted the model, it predicted the label as atheism, but the kind of words on which it has put importance are like God, this, or I think the color indicates which class, green, yeah, okay, so the green for Christianity and magenta for atheism. So that's why but like one thing is over here is, like, it has put importance on the word God for atheism. So I think that's how we can understand that the model is not working properly, because it doesn't go with our intuition. So that is one example. Okay, now there is another local explanation algorithm similar to Lime, that was SHAP. So it uses a game theoretic approach for generating explanations, but essentially it computes Shapley values, which was an already existing concept in statistics. But it also eventually shows the importance of different features in a particular algorithm. So what it does is that the Shapley values compute the conditional expectation function of the original model. So Shap values attribute to each feature the change in the expected model prediction when conditioning on that particular feature. They explain how to get from the base value of FZ, which is the original model, that will be predicted if you did not know any of the features, to the current output. Now I will show an example through which you can understand like how we can use SHAP in NLP. So in this, this is a movie review classifier, and like in this diagram here, they are trying to find the importance of different words estimated by this movie review classifier. So as you can see, the increment or decrement brought by each word is shown in the plot. For example, the word amazing with TF-IDF. So that the left the y-axis shows the TF-IDF value of each word also. So the word amazing with its TF-IDF score of 0.086 contributed to a 0.06 increment of the prediction. If it's positive, then it's what like we have shown here, both positive and negative contribution of the different words. So now we'll talk about some example application of LIME in IR. So this is the algorithm that was proposed to explain a retrieval model. They call it LIRME. So it creates different variations. First, let me explain what this model does. So given a pair of query and document, it tries to predict the words that are important by that particular retrieval model. So how does it work? So it creates different variations of a document B using different sampling approaches. So I'm like, the way the LIME was working, it was taking a neighborhood. So that particular neighborhood, this particular algorithm creates by creating the variations of a particular document by different sampling approaches. And then this particular objective function is trained. So what this objective function essentially does is, as you can see here, this row di dash. So di dash, D is the original document and di dash is the subsample document, which has been like the intuition is that it has been sampled from the neighborhood of D, and row di dash is measuring the similarity between D and di dash. And as you can see that the objective function is weighted by this distance function, as it is done in case of LIME also. And it tries to learn the essentially the explanation vector, this theta vector will generate the explanation. And so what it tries to do is it tries to learn the same value as the score of the original document given by the retrieval model. As you can see, it tries to minimize that distance. So theta is a p-dimensional vector showing the importance of a term, t in the scoring function. And the dimension of the theta is depends on like how long explanation we want. If we want to explain with 5 words, then p will be 5. If we want to explain with 10 words, it will be 10. So that's how this whole thing is trained. Now, these are the different sampling approaches they have used. So the first one is the uniform sampling, then there was bias sampling, and then there was masked sampling. So in uniform sampling, they sample terms with a uniform likelihood with replacement. And for bias sampling, they set a sampling probability of a term proportional to its TF-IDF weight, seeking to generate subsamples with informative terms. And for mask sampling, it is specify a segment size, say K, and then segment a document D into D by K number of chunks. Each subsample can comprise of a set of chunks. So so that's the kind of sampling strategy they have used. So in this particular work, obviously the similarity between the documents was taken into account, but whether the subsampling version is, obviously there is similarity between two documents, but whether they were like the subsamples were also relevant to the particular query or not, that particular thing was not taken care of by this subsampling function. So this is the example explanation diagram. So you can see the output of explanations for 3 different kinds of sampling. So the uniform sampling, TF-IDF sampling, and mass samples. So as you can see that for for a particular query and document, uniform sampling shows importance to the word like agent, undercover, and I think the relevant document was about counterfeiting money, and the y-axis shows the x-axis shows the explanation weights. And so there is a similarity between the explanation terms predicted by the different sampling approaches, but the TF-IDF and the mass samples has performed better than the uniform sampling approach, which is quite intuitive. So the evaluation approach used in LIRME was, there are 2 different kinds of evaluation approaches used. That one was the explanation consistency, and the other one was explanation correctness. So in explanation consistency, a particular choice of samples around the pivot document D shouldn't result in what it does, it shouldn't result in considerable differences in the predicted explanation vector. So they compare the correlation between the predicted and ground truth of ranking terms. So they know for a particular query, we have already judged set of relevant documents. And from those set of documents, they can compute the contribution of important words, and they can kind of have that kind of ranking of terms. And this particular explanation algorithm will also predict a rank list of terms. So the correlation between these two lists were computed. That was giving us an idea of the consistency of the explanation algorithm. And a second approach was explanation of correctness. So what it does is it computes the similarity between the explanation vector terms and the relevant terms. So this is the same set of terms, but they're computing the similarity between these two vectors. Okay, so this is another approach where we are explaining document. This is another explanation algorithm. We are explaining the document scores within and across ranking models. So here the explanation units for this retrieval model, the explanation units are the fundamental features. We know that the explanation units are the fundamental features of a retrieval model. So some of the example features are term frequency, document length, collection frequency, and semantic similarity. So this is a kind of global explanation approach, but since it kind of uses similar kind of regression architecture, so that's why I tried to. Okay, I think. Okay, I think there is a mistake. I will come back to this algorithm later. Then I now will move forward to the next explanation approach. So the next explanation approach. So initially we were talking about feature importance based approach. The next explanation approach is rule based explanation. So the local decision boundary that we are showing in that circle may not always be linear. So that's why this kind of rule-based explanation approach was proposed. So it identifies the condition under which the classifier has the same prediction, same kind of prediction. As you can see in this diagram, that in the right-hand side of that part, they have chosen a particular condition, and it kind of have a consistent linear prediction in that particular region. So it is based on a particular, it's not only on the neighborhood, it's also based on a particular condition. So, and based on that, then they try to explain the model with some rules. For example, this part of speech prediction model, it shows that they predict the word play as a verb if the previous word is particle. The example instance is given over there that I want to play ball. So play ball. So, and similarly, if the play is predicted as noun, if the previous word is a determiner. So I went to play yesterday. So based on that, so that's how they are showing the different rules based on which that particular prediction was done by the model. Now comes the
question. This the previous slide once. So here that grammatical thing is coming, right? So that means I need some prior knowledge of grammar.
Yeah, so it's a parts of speech tagging model. So yeah, obviously we will have the knowledge of the context, the sentence for all the words we have the information that we can run a post tagger and get the corresponding parts of speech.
Okay.
And based on that, we are.
But even if I take the frequency, term frequency and all, so I need to filter out, right? Before, like.
Yeah, that's what the condition. That's what they are calling as anchor condition. You have to find some conditions, based on which you will filter a certain set of instances, and then you will try to explain those instances based on those rules. Okay. You will try to find it will be kind of a decision tree kind of thing. Okay. But before applying that decision tree, you will filter the points based on some conditions.
So some data visualization is it?
Yeah, that's using that boundary decision. You can see the red circle. They found that linear kind of thing. So based on some condition. So I don't know whether I have the example. So there is another example where they are predicting salary. So there is a model which predicts a person's salary. So then what they are doing is they are taking all the set of input instances where the salary is less than 50K and then trying to explain that. Okay. Because based on the boundary, they found they have this, they can fit a decision tree kind of thing over there. I mean, this kind of rule, as you can see, here explanation is based on rule. Previously, we were just showing that these are the important features, but here we are showing the rule. If this happens, then you will do this. Okay. It's a kind of decision tree fitting into a particular region of the boundary.
Okay. But it will be more difficult if we suppose if we take small, shorter text formats like tweets. then that
Yeah, we have to
explanation
like-
would be very tough. And
Yeah, well, like we have to find like what feature is suitable here. I mean, it's not that always we have to find the parts of speech thing. We have to find some feature which also makes sense in the context of the problem. As I said, like for the salary prediction problem, the condition that makes sense is like whether the salary is within a particular threshold. I'm interested in that particular. So yeah, based on that.
How does it work for classification of it? Like, say, for example, you have spam which is not classified.
Yeah.
What kind of rules do you generally put in?
Yeah, so think of like what are the different features. So one thing obviously you can do is like you can try to explain the spam ones. You can filter all the spam ones and try to explain that one. Like if this is happening, then it is predicting as some spam.
What kind of outputs you get? Like, say,
Outputs will be like this. Like if this particular is feature, like suppose if this word is present in the tweet, then I will label it as a spam. So that's how the explanation will look like.
how is it different from the local other?
It is also one local kind of explanation. Local is the broader category under which all these explanation methods are coming. Now, previously, what I was explaining, there we were saying that this feature has this much importance. So suppose we had 3 or 4 features and we were ranking the features like for predicting this particular tweet as spam, a particular email as spam. This feature has the highest importance, this feature has the second importance. So that's why we were communicating with the end user. But here what we will say that if this particular word is present in the tweet, then we will label it as a spam. So you see, there is no weight over here. It's just kind of if-else condition. I mean, the decision tree that I showed, so it's a kind of decision tree. Yeah, this is the decision tree. So it will be kind of some kind of decision tree. Here we have hierarchical of conditions. I showed over only one condition, but essentially we can come up with 1 or 2 conditions, but it will be conditional, not, it's like the importance is this much. It has to happen. That is the difference.
So another question, like just go back to the application of Lime in IR setup.
Yeah.
So there you are saying like TF-IDF based sampling. So any idea like what form of TF-IDF functions were used? Like, so depending on the TF-IDF, term weighting setup.
I haven't checked, but my assumption is like actually in detail, but my assumption is that TF-IDF with, I mean, like you can do it any method. It eventually you will take the score and based on that you will sample the terms. Like if the higher, like I mean, obviously if a particular term has higher TF-IDF weight, it will have more tendency to, like with the sampler will have more tendency to sample that
Case the
particular
probability
term.
of sampling a term W depends on TF-IDF of that term W divided by summation of all the other terms. You normalize that. That's
Yeah,
the
but
probability.
if your TF-IDF weight function changes, so this biosampling will change.
Yeah, so these.
Your explanation will change.
So it's more likely to sample term that is more important, right?
Yeah, the expression will change, and
Expression will
that's
change, right?
separate. But if you see the output, the different things are not. It's not radically different. All the sampling strategies are not radically different. So my intuition is that if the retrieval model is working, it's a robust model. It's working well. Whatever sampling strategy, there shouldn't be heaven and hell difference between the explanations. Obviously, there will be some level.
Right.
And based on that, obviously, you can always build a robust explainer model which will not
Right.
change.
Right. So maybe now it's a good time for the room to ask questions before the speaker moves on to the next topics. I think there is a lot more to discuss.
Yeah, I mean, you can always ask questions. Stop me and ask questions.
Yes, if you want to ask some questions about Lime or this algorithm itself, just feel free to ask questions.
So.
Yeah.
So actually in Lime algorithm, like, so let's say we try to do classification for in health domain. So let's say some classification. So we take some features like the symptoms. So like we take some set of symptoms.
Yeah, I showed the example
Yeah,
initially,
yeah.
infectious.
So in that, like the features are pretty different. But when we go for some applications like NLP, so over there, like apart from word features, like if we go for backup words, then we have a set of features. But when we go for word embeddings, so over there, that features are not interpretable by humans, like because word
Yeah,
embeddings
yeah.
are. So
So,
in
see-
that situation, what more can
Yeah. So I will talk about a lot of other explainable approaches where we can deal with that kind of thing. But for Lime also, essentially what you can do is, I mean, so that you are taking an embedding, your model is taking an embedding, but you can have one human interpretable feature version of that particular input, right? And essentially you can try, based on those features, you can try to train a regression model. You have to just mimic the prediction. You know that document 1 has this embedding and document 1 has also this kind of human interpretable. So those two are kind of mapped, like 1-to-1 mapping is there. So now you can train a model based on that human interpretable feature version of T1 and the prediction and try to see. So that will also kind of give you an idea based on some human interpretable features that what the model is giving, and because you are eventually mimicking the model in that particular local region. But apart from that, also like this, you will see these saliency maps and all. They are trying to explain that kind of because they work in the image domain, so those kind of vectors and all out there. We can do something like that. I have one example where they have tried to explain the I think embedding algorithm. I'll come to that. So there you can see.
But even if you're using embeddings for Lime, that's something that you can use, right? Because that's the masking process in Lime. That's what it takes care of. Because if you're masking words, so what is it trying to imply that, okay, so if I remove this word, what's the effect of removing this word on my class prediction? So if I have a softmax, let's say over 3 classes, and if I remove a set of words for which the probability vector changes a lot, so I know that those words will be more important. This is something that Lime utilizes. So if you remember that diagram, which was shown, so you have a point for which you want to predict the importance of features. In this case, the features are terms, right? So when you sample documents from around that region, they are not real documents, but they are the masked documents, right? So you have this current document, you mask out terms. And then that process gives you the importance estimation over the terms in the actual document. Right.
Let's move ahead now because it's already 12.
Right.
Oh,
You start.
oh.
We can have the discussion later.
Okay. The second, I think then I have a lot of slides. So the second approach is the saliency maps, and it has been very popular in the image classification domain. So I will just go briefly over this. So what it does is what part of the input is important for output, and it depends on the gradient. And it has been like as I said, widely used for classification image classification problems. It is also known as heat map or feature attribution approaches. So the different variants of the saliency maps approach are input gradient, smooth gradient, and integrated gradient. But initially there was not such application of saliency maps on like NLP or that kind of thing, because like we have the discrete terms and all. But recently, as I said, that for explaining some kind of embedding algorithms, they have used the saliency maps. So this is one example where they are explainability, we are beyond classification. So they are trying to explain the large language models. So I forgot to include the paper reference over there. If anybody wants, then I can do it. So what they are doing over here is they provide contrastive explanations for large language models. So explainer looks for salient input tokens that explain why the model predicted one token instead of other. So contrasting explanations are better than non-contrastive explanation that they have showed in their paper in verifying grammatical phenomena. So this is the example. What it does is like, so suppose the input was, can you stop the dog from, and it was predicting barking. So now what this saliency input gradient based approach is doing over here, it is trying to predict like why did the model predict barking. So that is like, it is not, it is just asking that question. And these the red ones are the most important tokens. I mean the gradient of rain, and these the blue ones are not so important tokens in this particular context. So first, like they can answer this kind of questions using this saliency map technique, and they have also can explain that why did the model predict barking instead of crying. Similarly, why did the model predict barking instead of walking? So these kind of things they have. These are they calling as contrastive explanations. So these are the things that they have tried to explain using the saliency map techniques. So they focus on explanations that communicate why a computational model made a certain prediction. So what are these saliency scores over the input feature XI is to reveal with which input tokens are most relevant for a prediction. The higher the saliency score, the more the input is supposedly contributed to the input token has supposedly contributed to the model output. So here I have shown the formula for computing the saliency score. So it is essentially taking the derivative with that particular token, and this Q of YT given X is essentially predicting the model predicts a target YT instead of the foil YF. So that's how this saliency score is computed. There comes the second approach, which is the prototype-based approach, where what they do is explain a model with natural or synthetic example. So so here the nature of explanation is different. Here they are saying what kind of models it is going to misclassify, which input maximally influence and output. Sorry for the title. So these kind of things can be answered with the prototype-based approach. So here is the example. So generally, this prototype-based approaches is done by the influence function. So here you can see that the input was a Junko bird, and the model eventually predicted it as a Junko bird. So now they are trying to understand that which training points have the most influence on test inputs law. And they kind of see that these are the kind of similar birds to Junko bird, and the model used these particular training samples to eventually derive to the conclusion that the particular bird was the image is a Junko bird. So that means the model is working well. If instead of these these birds, if we would have got something like completely different from the Junko bird, then we would have to think that the model is not working well. So what this influence function is a statistical tool used in robostatistics for assessing the effect of a sample in the regression parameter. This is the example of this is the equation describing the influence of a sample on test input loss. Here H is the Asian vector product, and the challenge over doing this kind of influence function, this technique, is that computing Asian vector products can be tedious. Otherwise, this kind of influence function is very much useful in predicting the image classification, that what are the inputs which are most influential in predicting a particular output. Then comes the counterfactual explanations, how the counterfactual explanations work. So I hope you people are getting the point how the notion of explanation is changing in different kind of approaches, like the saliency map and the prototype based and the counterfactual. So what counterfactual is doing, that what features need to be changed, how much to flip a model, how we can flip a model's prediction, that it tries to predict. So as you can see that this is a loan prediction problem. So we give the applicant's feature as an input, and it predicts whether we should give loan to that particular applicant or not. And for this kind of loan prediction problem, counterfactual explanations are very useful, because then we can say the applicant that particularly for this feature you didn't get the loan, and then he can work on that. He can take the recourse. For example, here he's saying that increase your salary by 50K and pay your credit card bills on the time for next 3 months. Then you will be given the loan. So this kind of that's why this counterfactual explanations are very useful in this loan prediction domain. So there are different approaches for counterfactual explanation. So one is the minimum cost counterfactual. One is the feasible and minimum cost. So sometimes the minimum cost is not working because it's not feasible. That's why this feasible and minimum cost counterfactual came. And then also some causally feasible counterfactual. Suppose like a loan prediction explanation is saying that you have to change your credit report for the last 6 months. That's not possible. So that's why we have to opt for also causally feasible counterfactual explanation. So now I will start the approaches for global explanations. Can I take a break? I'll take 10 minutes. What's the time?
Well, I don't think we need to stick to the time schedule very strictly, right? I mean, we started a bit late, so it's okay. It's okay to have lunch.
We'll resume at 12:16.
Okay, so we will start at 12:16 again.
Okay. And
You need to repeat the content
Yeah.
because it doesn't.
so these are the different global explanation approaches, the collection of local explanation, model distillation, and representation based. The collection of local explanation is a very simple one where we just aggregate the local explanations and try to come up with a global explanation. The global line algorithm that I showed, where it was trying to choose the maximum coverage feature, that is an example of this collection of local explanation ones. I will now describe the collection of local explanation application in for IR. So for any ranking model, the features like fundamental features like the term frequency, document length, collection frequency are very important. So here we are trying to explain a ranking model in terms of these features. So what we do is for each retrieval model and for each query, we train a regression classifier based on these fundamental features. And so this is a local explanation, you can understand, right? So for each query and the document, we are training a classifier. And then we choose randomly k number of queries for a particular model and then take the average weights learned across k queries. That's what we can say, that that particular retrieval model gives that much importance to that particular feature like term frequency. So this is the box plot of the parameter vectors for BM25, LMGM, LMDirichlet, and DRMM from left to right. Since we were also considering neural models, so we took semantic similarity as also one of the features because neural models use semantic similarity. So the box plot shows the range of weight values that we got from the regression model. As you can see, like for DRMM, the range of values that we got for term frequency was like huge compared to the other features. But for statistical models like BM25, LMGM, and LMDirichlet, this variance of values is far less compared to the retrieval model. So that is one observation that we got from this explanations. Now, with this approach, also we try to explain that why does a particular model M retrieves a document D1 at rank R1 and the other document D2 at rank R2? I mean, why is this ranking position difference? So without loss of generality, we assume that R2 is greater than R1. So to answer this question, what we do is for a particular feature, the contribution of that particular feature is defined for a particular document by this formula phi x. So what we are trying to do is for all the terms, query terms appearing in the document, we just sum up the contribution of the particular feature, for example, term frequency, using this phi x function. Now, once we have that total contribution of that particular feature, like for example, term frequency, we compute the relative drop, which we show it as delta x d top. So like suppose we have two documents, D1 and D2, we try to identify like what is the relative drop in this contribution, this phi x function. Now, once we have computed this delta function, then we try to compute the fidelity score. So what this fidelity score is trying to do. So here theta is the like the weight vector that we have learned for that particular model, and like this data is d top, all these values are coming from this relative document measure. So we do pointwise pointwise multiplication in this zeta function. So so eventually zeta is a vector. So what it does, I think we have the diagram, is that so if zeta like for a particular feature, like for example term frequency, if this particular like this delta x d top is positive, and we also know the sign of theta is also positive, then we can say that term frequency was the reason for which like the particular document D1 was in the lower rank compared to D2. Similarly, and for so why like this theta vector is showing the importance of different features. So if the importance is positive, then we can say that if that particular feature increases, then the model score will increase. But if that particular weight value is negative, then you can say that if the particular feature increases, then the score decreases. So that's how we try to show. And this is the diagram showing that with respect to the features like term frequency, So this zeta XYZ is the town frequency, document length, and collection frequency. With respect to these features, we have compared a pair of documents and show using this heat map, we have shown like where the increase of a particular feature has contributed to the higher rank of a particular document. So this has been computed for BM25. Then we have also tried to explain this question that why does a model M1 retrieve a document D at position R1, whereas the model M2 retrieves D at R2 for a particular query. So one thing I haven't mentioned, that is like one can think of that, okay, for we have done this for both statistical and neural models. So one can think that for statistical models, we know the feature value and we know how the score is computed. So why we are going for this explanation things? Yes, we know the score, how the score is computed, but if we are asked particularly these kind of questions, then we do not have any direct answer, because we know the whole scoring formula, but we do not know that exactly for which feature that ranking difference is happening in different models or within a single ranking model. So yeah, so for this second question, we also do the similar kind of thing. So as you can see, this delta SQDM, what it tries to measure is that it tries to measure the difference in the contribution of the particular with respect to the top document in each model. Now, once this delta is computed, then we compute this zeta value for a pair of models M1 and M2, which is essentially delta S of DM1, M2 and M1, M2. So, like, there are a lot of maths here, but essentially what we are doing is equation at the end, like in equation 8, if we get positive values for a particular feature, then we can say that for that particular feature, because of higher value of that particular feature, this document D was at position rank 1 in M1 compared to whereas it was in rank R2 in the model M2. So now I will talk about the model distillation approach for global explanation. So in the model distillation approach, what happens is that suppose there is a predictive model and it predicts the levels, as you can see. So it tries to create a simple interpretable model which is optimized to mimic the model predictions. And like line, it is not focused on a local neighborhood. It tries to mimic the whole model globally. That's what is known as model distillation for global explanation. And like, for example, here, this is an example case of model distillation used as a global explanation. So as you can see, it has kind of create a customizable decision set. It is saying that if the age is less than 50 and male is yes, and if past depression is yes, and like this, all this condition holds, then you can see that the model is healthy. So like the rule-based approach in local explanation, we are doing that locally, but here we are doing the same kind of thing globally. We are trying to define different conditions, and based on that, we are defining this customizable decision tree and saying that the model works in this way. I mean, it's not that it is always possible to map every complex model to this kind of customizable decision trees, but this is one way of doing it. If it fits, then we can explain the models in this way. And here there is no importance of a particular feature. It's just all the if-else condition of a decision tree. So then there is this representation-based approach. It estimates the importance of intermediate layers in a deep neural network model. So what it does, it identifies the human level concepts and then estimates the response of hidden variables to this concept. So and then quantify the alignment of hidden variable concept pairs. So some of the notable approach in this area include the network dissection and TCAV. So okay, so what it does essentially, what it means is that you have some human level concepts, and it tries to identify what is the change in the like in the output with respect to this level. And like if you change the hidden variables, how these like these features are affecting the output level. So that's how that is trying to define like, the importance of the intermediate layers in a deep neural network model. This is an example of this is an example of post-hoc explanation approach to interpret a network embedding. So since here it is also trying to explain a network an embedding, so that's why I put it into this representation-based approach. So it explains in terms of taxonomy. So what it does is that so these are the like in the figure A, those are the normal vector projections of the embeddings. So what it does is it creates a cluster, and it have already some predefined taxonomy. As you can see, the 0, 1, 2, 5, 6, 3, 4, these are like this is a taxonomy, the human defined taxonomy. We know like what is the hierarchy, and like the hierarchy was chosen by the humans. Now, once the cluster has been done, then we try to map it with this kind of what you can see in F. We try to map it with this taxonomy structure. So what we can say from this kind of hierarchical graph structure is like in this graph, we know what this particular word means. So like suppose this is the end node, we get the embedding over here. And we also know from this taxonomy, we also know the like the actual token value. So suppose there are some topically related words. So we exactly know that in the leaf node embedding, what are the like it also captures some kind of inherent embedding, like hierarchically. That topical hierarchical structure is captured in this graph, and that's how we explain that this embedding also captures like these concepts within this representation. So yeah, this is an example of taxonomy-based representation.
So I didn't follow that. At least can you give an example? For example, if you
yeah, suppose like the word king. So it should have also some meaning of male, right? In the in the embedding representation. So that's what it is. So suppose if you see king over here, you will also see male. So like king, boy, and all these words are related to male. So suppose this is the male word, and you will see that this king, boy over there. So you are explaining the user that the embedding of king also captures the inherent meaning of male. And suppose there may be some hierarchy, and this hierarchy structure is coming from here because we have already some predefined structure.
how do you build this hierarchy?
Hierarchy is a human defined.
For example, if I'm working on some classification or some, how do I build like?
So it depends on the data. Okay, so the kind of words that you are using, you will build some kind of hierarchy first, and you will cluster the embedding over here. So clustering gives you this kind of thing. Then you will join those dots which are connected over here, because you know that those make sense. So it is not obviously that you can capture the whole actual hierarchy, but it will give you some kind of idea that within the embedding of this word, you are also capturing these meanings, like which are like hierarchically up in the structure. So that's what the kind of motivation. Like for example, the spam example that you said. So there must be some specific keywords you are related to your domain, right? So you can manually create a hierarchy over there. I don't know whether making a hierarchy makes sense in that domain. Obviously, it has to make some, but it must be, because the like if you are using embedding, there are semantically related things, and there must be some kind of connection between them. So those keywords, you first create a hierarchy, and you have the embedding for those tokens, and then you cluster, and then you join based on the hierarchical structure. I mean, so the utility of this structure is that you are not joining every points over there. You will join only those points which are connected over here, and that will give you an idea. So someone was asking like how to understand the embedding. So this is one way people have tried to explain the embedding. So now over the evaluation approaches for explanations. So like we can categorize this evaluation approaches into this three different areas, like application grounded evaluation, human grounded evaluation, functionally grounded evaluation. You must have understood from the like the definition, like in application grounded evaluation, we need the real humans and real tasks. In human grounded evaluation, we need real human, but simple tasks also works. And the functionally grounded evaluation, there is no real humans. We use proxy tasks. So for example, the Learme algorithm that I have explained, so they have used this functionally grounded kind of explanation category. and more specific, like the arrow shows, like obviously the application grounded evaluations are more specific and costly. For example, you want to explain the one law domain application that I showed, that for the charge prediction thing, you need real humans and real tasks to actually evaluate the application. I mean, that is the most preferable way of going about it. So now these are the different ways. So those are the categories, and now these are the different ways you can do. So one is the understanding the behavior. So this is a very simple intuitive technique. So suppose your explainer for the feature importance explainers. So what it does, it gives you a set of features in the descending order for a particular prediction. So what you can do is, I have shown the example with image because it will make much more sense over here. So you can keep on adding those feature points to your classifier and try to see how the performance is improving. If a particular thing is an important feature, obviously adding that particular feature will drastically improve the performance of the classifier. As you can see that it is showing that it was trying to delete some pixels. So suppose the classifier showed that the surrounding pixels are very important. So they have just used from the original picture, they deleted the rest of the, only kept the important features, and that was the performance level. Actually, it is a line plot. So they actually went from this different features. And where they are using, so deleting a feature, they are deleting the old feature, that you can see the performance that this is the performance is not working well. So if you are saying that you can work it as for deletion or also insertion, you can do both way. So if the performance improves with the addition of these features and the performance degrades with the deletion of these features, then you can say that it is following the intuition. And the explainer is following the intuition, and that is one way of evaluating an explainer. The other way is predicting the user behavior. So check whether a user can learn about the model's behavior from explanations. So there is this data and classifier, and it has a prediction and explanation. We show it to the user. Now, like in human mind, that user also learns something from the explanations and predictions. Now we have new data and the prediction. Then we ask the user, then what do you think should be the output of the explanations for this new data, given that you have already seen the previous explanation? Now he will say something. Now based on that, and we have also our explanation, generated explanation. See if we can compute overlap, accuracy, or that kind of thing, depending on that. And that is one interesting way of evaluating an explainer using a human in the loop. It is also another thing where we are asking that, do you trust, we are asking a human, do you trust this model? Could they compare between different classifiers? So what they have done, so this is the image classification. We have the original classifier and explanation. And we have some, we have part of the classifier some way, and we have also the prediction and the explainer. We are showing the explanations to both the user, whether, so we can ask different type of questions. Like which algorithm is better, whether they could, like sometimes this also happens because for adversarial attacks, that the explainer doesn't show any difference between the two explanations. In that case also, we know that the explainer is not robust. And we can also ask the user that, like which algorithm is better. If suppose for the user, it looks like that this explanation is, in ideal case, this should be the explanation, which makes, like, for example, yeah, this doesn't make sense, it makes sense. But if suppose like somehow because of some adversarial attack, this explanation is good and the user chooses this one, then we know that the explainer is not working. So this is also another way of using human in the loop thing. So these are the limitations of evaluation for explainability. Because evaluation setup is often very easy or simple or unrealistic. Bugs or obvious artifacts classifier are different from each other. Instances or perturbation create out of domain points. That's what I was trying to mention. Like we can always subsample and create different type of points, but if it is out of domain, sometimes those instances, or for example, for Lime, we will sometimes create this perturbation and create a neighborhood. But if those points, those are out of domain points, then it doesn't make sense to evaluate those explanations and also train a classifier based on explainer based on that. Sometimes these are flawed. So, for example, the model explanation is the model explanation same as human explanation? It doesn't always go hand in hand. So that is also one problem. Automated metrics can be optimized. So that is also one problem. And user studies are not consistent, affected by the choice of user interface, phrasing, visualization. This is a problem of any user-based studies. So that also comes with this. And sometimes, so because of this, these conclusions are difficult to generalize. So that is the limitations. So these are also the limitations of post-hoc explainability. So, so the limitations are faithfulness or fidelity, fragility, stability, and usefulness in practice. So some explanation methods do not reflect the underlying model because, like people have shown with the adversarial attacks, the explainer was working perfectly well, but the model was disturbed. So in those cases, it was not that means that explanation methods was not reflecting the underlying model. Similarly, the fragile post-hoc explanations can easily be manipulated. Stability, slight damages to inputs can cause large changes in explanations. That shouldn't be the case. And it's useful, for example, for in IR, like a retrieval model explanation, this, I'm not aware of any work where they have tried to check this stability thing that like how slightly changing to input is changing the explanations. Like similarly, the useful in practice, unclear if a data scientist, like, so initially we say the whole motivation for this explainability field is to make more trustworthy AI models, but it is still unclear if a data scientist or end user can use explanations to isolate errors, improve trust, or simulate the model. Only for the counterfactual explanations, there are works where people have tried to use the recourse to change the model. But other than that, there has not been much study where people have tried to see that how much useful the explanations were to the end user eventually. So these are some of the works. These are some interesting things that I wanted to talk about explainability. So now that I have given kind of overview of the explainability, the approaches that we use. So one interesting direction is adversarial attacks on explainability. So we modify input with small perturbation. The model output shouldn't change. And we observe the change in explanation under adversarial attack. Commonly known attacks are shift attack, augmented loss, function attack. I'm just simply talking about the names. I'm not giving the details. Passive and active fooling loss, augmented attack. So there are works which show that Lime and Schaff suffer from these types of attacks. I mean, the output won't change, but the adversarial the explanations are changed. Like that's why some defense algorithms has been also developed to handle these adversarial attacks, which are hyperplane method, autoencoder approach to prevent explanation manipulation. This is one interesting direction for explainability. There has been some work where people are training and explaining the explainer and the model simultaneously. So the first work was there is one notable work which is L2X, which is learning to explain. So they propose an information-based information theory-based framework for an instant voice feature selection. So what they do is given a feature vector, the model attempts to create all possible subset of the feature vector, and then for each variant, the model computes the mutual information between the response variable and the input, that subset vector. So higher the mutual information denotes higher dependency between the output and the input feature subset. So eventually the explainer learns the importance of different features with this mutual information optimization thing. Now, obviously, suppose a feature vector is of size k, it is not possible to create all possible subset feature combination. That's why they use some kind of Gumbel distribution to tackle that issue. But yeah, eventually using this different kind of subset of feature vectors, they try to optimize the mutual information between the response variable and the input. So this is the output of that L2X output for a classifier. So here you can see that the model is predicting positive and negative, the different sentences, and it is highlighting those set of words or phrases which it thinks as important for that particular prediction. So it has also learned to predict that positive and negative labels simultaneously along with the explanation. So I think the usefulness of this method is there are a lot of works where people have tried to train explainer and the model simultaneously, but in those cases you need some ground truth explanations, which I will talk about in the next method. But in this work, you do not need the ground truth explanations. But with this mutual information optimization thing, you can train the classifier and the explainer simultaneously. I think that is one of the usefulness of this method. So this is the method where they have used a rationally aware contrastive learning-based approach to classify and summarize crisis-related microblogs. So this model has two stages. So in the first stage, the model learns to extract rationals using a multitask architecture. So they have two tasks. One is learning the levels, and one is learning the rationals. And these rationals, they have some like user annotated rationals already, and based on that, this model tries to learn that. Now, once the classifier learns in the first stage, what they do is like they extract rationals for all inputs, and they use those rationales eventually to the final prediction model. So that's the kind of structure. So here is an example of tweets, and the blue ones are the like the rationales that has been annotated by the users, and that's how they are using those kind of rationales to eventually improve the performance of this classifier. So this has been also another direction of work. So here are some of my comments on explainability in NLP. So that classification problems can be explained with line-like architecture in general, and counterfactual explanations are useful for like from all the different approaches that I discussed. The counterfactual explanations are mainly useful for text generation models, because we need that kind of explanation for these text generation models. So while opting for any particular explainability approach, we should think about that what kind of, first we should think about like what should be the notion of explainability for that particular problem description. And these are the comments for IR. So it can be, so like IR models can be explained based on the query document pair. These are local explanations, as I explained in the work limit. And it can be also explained based on the features like term frequency, document frequency. These are global explanation. The work that I explained. So it was trying to explain the retrieval model based on the fundamental features like term frequency, document length, collection frequency. I think one interesting thing about IR is that we can explain relevance and non-relevance class separately. Because for relevance class, what matters is like what are the words which are present in the retrieval model and for which the model has predicted given higher score to the document. But for non-relevant class, we do not need the presence of documents. We want to know what are the absence of the words or phrases or topics or concepts because of which the model didn't put it into the higher line. So that is one interesting thing about explaining IR models. And as I said, like counterfactual explanation is more suitable for non-relevant documents. Yeah, I think that is one interesting thing about IR explanation. So this is also another direction of work in explainability. This is some theoretical work. So I'll just give a brief overview. Like what this says is like it tries to explain like which explanation should I choose. So they propose a again I forgot to. So this is I think this is a 2021 or 2022 work from Himabindu Lakaraju. So which explanation should I choose? So they propose a linear function approximation framework to formulate any explainability algorithm. And so their idea is that popular explanation algorithms like Lime and Shapley and all these can be mapped to this framework by adding some kind of drawings. And then they propose this no freelance theorem, which says that for explanation methods, which demonstrates that no single explanation method can perform local function approximation faithfully across all neighborhoods. So what does that mean? Like, so we have to always choose the explainable algorithm based on the like the local approximation function, the neighborhood function we are choosing. The disagreement occurs because different methods approximate the black box model, but different neighborhoods using different loss functions. If the explanation model preferably perfectly approximates the underlying model when it is able to do so, then it should be chosen for explanation. And like here, they are showing the difference between the different explanation approaches for same pair of examples. So like from this L1 distance function, so this is they're computing the difference between the generated explanations. So what the eventual conclusion is that for continuous data, use additive continuous noise methods, which is like smooth grad and Gramier cadence. And for binary data, I mean, like by binary data, I mean the predictions are binary. Use binary noise methods, for example, line. And within each domain, choosing among appropriate method boils down to eventually determining the perturbation neighborhood. So how you are computing the neighborhood, that distance function, that is very important for generating a useful explanation. So that is the kind of takeaway from this paper. I think if you want to apply in kind of IR or NLP, so you have to carefully choose the distance function. So beyond classification, people have also tried to explain the reinforcement learning framework. So the way they have tried to explain is using the causal explanations of the behavior of the model of free RL agents. They also generated explanations of agent behavior based on the counterfactual analysis of the causal model. So for example, here you can see that the question was why not build barracks, and it is showing that by explanation, it is showing the giving the causal explanation of that particular counterfactual explanation of that particular question. And there is also, they have also tried to explain using model distillation approach, using soft decision trees. They have tried, that is also one way that they have tried to explain the reinforcement learning framework. And sometimes they have also used summarize the agent behavior by identify the important states in a policy. This is kind of similar to the approach that I was saying, like you can explain the different layers of a deep neural network for a kind of image classification of that kind of problem. So they are trying to explain that kind of thing. And this is the kind of broad level overview of the different ways the different way the people have worked on explainable IR. So there are some feature attribution methods, there are some free text explanations, and with adversarial examples also people have worked on some post-hoc explanations. And in the ground truth IR properties, people have tried to check whether a particular model is following some axiomatic property or not. That is also one way of explaining the IR models. And there are very few work where they have tried to explain the architectures. The same way, like what is the importance of a particular layer or architecture in a particular retrieval model or something. So that's the kind of overview. And last time, end with this model. So this is a very recent paper that came out. This is a talk to model. So it is kind of changing the notion of explanation. Because still now we are trying to generate words, phrases, that kind of snippets, that kind of explanations. So here they are generating interactive explanations. So they have built a model, live demo system. So there are components like a natural language interface for engaging in conversation, and then it makes the ML model explainability highly accessible. So a dialogue engine that adapts to any tabular model and dataset and interprets the natural language, like whatever the components of any conversational AI agent, it has also that. And along with that, it has an explanation model. And it maps it to appropriate explanations and generate text response. An execution component that constructs the explanations. So this is the architecture. So I think rather than seeing, there is the live demo. Okay. So here they're saying I'm a machine learning model to predict whether someone has diabetes or not. So what are the three important features? Then the user is asking. It is showing the three important features. What's the distribution of glucose? So I'm like, essentially the idea of explainability was to bring transparency. So end user can have different kind of questions, different kind of notion about explainability. I think the idea is to combine everything through this kind of interface that they are trying to do, that you can ask any kind of questions and it will try to explain it that way. So yeah. Okay, so I guess that's all I wanted to share for today's. If anyone wants to ask any questions.
So you talked about line, right? So one of the comments was that we mask some of the words and things. But if there is a document of length, right? So if you mask randomly, like all the possibilities, there are 2 power n for the meetings, because for example, I work with like sentiment analysis and the movie is not good, or let's say the movie is good. So it's not only about fun good, right? It's the variables are dependent, not independent. So how do we work? How can we work on the?
Yeah, I understand your question. So the first thing is the intuition behind Lime is that you have to find that local neighborhood where you can feed the regression classifier. So you have to take that many neighborhoods. So that is a parameter. Okay, so while masking, you are creating eventually some variants of the input. Okay.
So can you explain it?
So while masking, you are creating essentially some variants of the input. So suppose D was the original input, you are creating D1, D2, D3. These are all the variants of the original. But you have a parameter over there. Once you can feed a proper classifier, regression classifier over there, you don't need to generate more samples. That's why you don't need to generate all possible subsamples.
For example,
So suppose you see that your regression model is working fine with 50 variants. Then you are fine. Then you got a classifier, you got an explanation model, explainer over there. You don't need to generate all possible subsamples. The idea is that you have to fit something in that region. And obviously those variants should have the similar prediction levels as the original one. And it is also true that like for your all possible samples, it may not have the same prediction. Yet we're working with all the models, so we have the similar kind of prediction. That's the kind of thing.
Usually there will be a subset of terms that are important, let's say 10 or 20. So if you sample a reasonable number of examples, right, that should inevitably be covered by those 10 or 20 terms. I mean, you don't need to, I mean, even if the document is of like 100 or 200, that doesn't matter, right? Because not all the terms are important.
but here example
Like for the atheism example that you have seen, right? So Christianity was the main word that was like affecting negatively the class, because the class is about atheism, but Christianity is about positive about God. So that was affecting negatively, but the negative influence was too high. Because if you remove that term, which is inevitably going to happen if you take hundreds of samples, right? You can get from those samples, it's easy to determine that the importance of that term is pretty high, because softmax distribution over 20 classes is going to change a lot if you remove that term. You don't need to take all the samples.
And one thing also, as I said, the distance function is very important. You are thinking that you always need to mask something. May not. You may use some kind of, suppose you have 50 tweets, and like you can take the nearest neighbor based on the embedding representation. That also you can use. It is not that like, suppose you have tweet T1 and you take that like 5 nearest neighbors and try to train a classifier. So you have some embedding for that particular tweet. You can take the 5 nearest. You can define the neighborhood in your own way. It's not that you will have to create some kind of subsample always. I mean, mask some token and create the variance. You can use the similarity cosine, like the embedding the similarity function or anything to define your own neighborhood.
So have people tried kernel learning for this?
Kernel SHAP is there.
Kernel set.
Even for live, you can use it.
It was in an original paper of SHAP.
It was proposed in the.
Kernel SHAP, deep SHAP.
Oh, okay.
Those are-
Yeah.
Even for line, you can do. You can define your kernel.
Actually, the context which you were like masking some words and trying to create another document, and then try to apply this Lime algorithm. So even I think SHAP algorithm is somewhere the other
Yeah,
similar.
they're the same. They're the same. It's just the way the SHAP values are computed. That is different. But the kind of the intuition is always the same.
When SHAP algorithm is something like which is computationally little expensive.
Yes, exactly. And that's why people have also tried some kind of approximation of those SHAP versions.
Such as small curve.
Yeah. I mean, I think still people are
Tree
working on
SHAP,
it.
deep SHAP, these are
Yeah.
approximation.
Yeah, people are still
You
working on
don't
this.
need to get to the n many subsets.
Yeah. Because that's not realistically feasible.
This was popular in the 80s for feature selection. They used to apply something called the branch and bound. So it's a discrete state space level. And then they used to do that for selecting documents. It's kind of similar to this, right? I mean, explainability is also like selecting documents.
So I have some context. I work with the financial based summarization models, like C2C models, versus models. So we trained our model, it's working fine, but how do we explain like?
Yeah, you saw that, like as I said, like for text generation models, you can go for the counterfactual. So I showed one example right there. It was saying that. So it was using the gradient based approach, the smooth gradient. So it's essentially the image classification initially used.
Yes.
That kind of thing you can use. Yeah. So it is using both contrasting and non-contrasting explanation. Here it is just asking why it has predicted barking, and here it is predicting why it is predicted barking instead of crying. Those are contrasting explanations.
But in summarization, what kind of outputs can I expect? Like say,
So that you have to think like. So in summarization, you can think like why the counterfactual part can be like why the summarizer didn't choose this particular sentence in the output, but or why this particular, like what is the influence, like I talked about the influence function. You can also do some that kind of thing, that what is the influence of a particular like what are the sentences which particularly influenced in generating a particular phrase in the summarizer. So this can be useful for summarization. Like what kind of explanations do you need? I think the best way to go about is to ask the end user what he wants to see. Ask any common person like what he wants to know. So there you have to fix like what should be the notion of explainability. And then you have to think about the approaches, all the different kind of approaches are available.
is there any library or any?
I mean, Lime and Shaps, they have that libraries. This OpenXAI, there is a tutor like they have this benchmark something there. You can try out a lot of different XAI. Yeah, I think give you the link. I mean, these are the things. But I mean, as I said, for the notion of explanation, you should ask the end user or think of yourself as an end user and think of this way that why do you want the explanation? You want to improve the summarizer or like why? So then the questions will come out automatically. So for example, as I said, for the retrieval model, the common people can ask that why this particular document has been retrieved by in the top rank by the retrieval model. That one common people can ask. But if the end user is an IR practitioner, he may think of that I know that this particular document has some useful, in terms of document length or something, it has very short document length, it has some informative words. Still, why it is not in the top rank? So that then the notion of explanation changes based on the end user, and then the explainability algorithm also.
Maybe one quick question. So what is the difference between causal machine learning and explainable? Are they the same? So now that we see a lot of thing about causal ML. So are they basically the same thing? So
I don't understand.
So you go to ICML, so you go to IR community, people talk about explain. ICML also talks.
Yeah.
But
So many papers.
last ICML, all the papers have been on causal ML.
Many papers are on causal.
Causal
Even there is a separate conference
Separate
for
conference.
causality and inference something.
Yeah, causality is very kind of a recent topic now. People are trying. I think to some extent, counterfactual is also similar to explanations are similar to the causal. I mean, I think there is very fine line between those kind of things.
Yeah.
The causality and correlation are kind of related, right? But
No, so that's the
causality is
definition
stronger
of
than
causality.
Causality is stronger than correlation. I mean, when you
No,
know the context,
that's not the question. The question is that when you talk about causality derived from a model, so isn't explainability enough for that, or do you need something else?
so explainability to my view is like, so when you are, so it's basically trying to find the correlation of the important features with respect to output, right?
Yeah,
So
maybe
what
this,
kind
yeah,
is-
what that one will,
Yeah, like
yeah,
for
exactly.
example,
This is
in this loan application, they are saying that you didn't get the loan because of like, suppose your pay was less and the credit card. So this is kind of causation, right? You are saying that these were the reason for which you didn't
Right,
get
exactly. So it has more to do the actual situation.
Yeah.
actual-
I mean, that's why it's like for IR, for non-relevant documents, this kind of explanation is very useful.
So maybe we are more interested in the relation between the attributes rather than trying to explain the output, right?
Yes. Because for these kind of models, that can help to, I mean, get the
more
applicant
physics
to,
of the,
get the
right,
applicant the,
of the phenomenon.
But counterfactual can only work for discrete features, right? I mean, if my features are not discrete, then
So
how
doing
can
even
I
causal
even-
is difficult.
how can I even talk about leaving out a feature? I can't do that. So what additional benefits for, this is feature-based learning, right? So what additional benefits can counterfactual explanations give in relation to say Lime? So Lime is also giving me feature weights. So how it should,
feature weights, but this particular thing is not giving me weights. This is giving me the absolute.
Relation between the.
Yeah,
but why is this more powerful than learning the feature
because
weight?
for
No,
this
no.
kind of stakeholder application, this
Yeah.
is very important.
It is
I
important.
want to know that, I mean, like, in IR also, I want to know why this non-relevant document, this document was not in the top key. Maybe as an IR practitioner, I am curious that because I thought that this document is useful.
Exactly.
And it is retrieving most of the relevant documents, but why it didn't bring it? I am not thinking about the presence of something, absence of something, what it lacks. And that is sometimes important for the individual.
I'm trying to see why it has come to that summary or whatever. Why it has come to that output.
But for Lime, if I get a high negative weight for one of the words, like say, for example,
No, it doesn't. For I'm giving a more medical domain example. Say,
Yeah.
So you want to predict whether somebody will have diabetes or not.
Yeah.
Okay, so as a doctor, I'm trying to figure out is there a relation between the glucose level and the hours of sleep.
yes.
But while in Lyme, I am trying to see if hours of sleep is important to predict
Yeah.
whether diabetes.
Yes.
Now here I am not interested in just to
It's
predict.
important or
Yeah,
not.
I am trying to predict what is the relation between hours of sleep and glucose,
Yeah.
not diabetes.
Yeah.
What has that got to do with counterfactuals then?
No, that's what
That's
it's
what
trying to do. Why that is
Right.
used. That's exactly what we are trying to do.
No, but here it's also with respect to output, right? I mean,
No,
Yeah, it's loan or not loan,
Yes.
accepted or rejected. no, nothing.
conditional on that.
Yeah,
Conditional
yes.
on that, but finally you are giving a counterfactual algorithm. I mean, why this is useful.
Yeah.
Yeah, I don't know. It depends on the application, as she has said, and
Yeah,
it depend on
I
the.
mean, counterfactuals is, I think it's more suitable for recommender systems, where they have this large.
No, people have used in other places also.
Yeah, I think there are a lot of work on this, these counterfactuals where people are trying to modify the model also based on this recourse they are saying, that based on the,
Yeah, for
This one-
example, this loan prediction. They're trying to.
yeah, here the applicant, and here I think we don't need to change the model. We can just say the applicant that you have to do these things. But there are, I mean, like, I think in some cases we can use as a feedback to change the model. If we see that the apps, suppose we are seeing in a model that the apps, if the person is of male gender, then we are giving the application, and if is female, if he is not male, then we are not giving the loan. So in that case, we need to
Tuning
retake the
that,
reports and
tuning
tune the
that.
model. So in that case, then.
That's what finance domain regularly
Yeah,
does.
yeah.
They regularly. So the
I think-
finance domain will regularly do that. So you are doing to say portfolio, say you are predicting whether the portfolio works or not. So then you design some attributes, then you go back and then you want to fine tune that. So then this kind of counterfactual will help.
And then you go the counterfactual generation algorithm, can it be like incorporated in something like online learning, something like that? So let's say, so the transactions can go day to day, like let's say someone applies for a loan application, and the bank actually accepts.
So you are asking that whether it can be deployed real time, right?
Yeah, so the thing is like, so whether that learning can happen on real time. So let's say, so then this bank, they try to generate some explanations manually. So then over a period of time, can we train a model in such a way that it starts like based on the
So
applications?
this is a local explanation based approach. So I think since it's local, it should be doable, but I'm not kind of expert in this area, so I can't say. But I think since a local explanation based approach, so like what is something different in real time? You have a limited number of examples. You should be able to train that since it's not a global thing.
How can we apply the same for GPT-3 and that's where it's completely.
So in GPT-3, what you want to do? So like, as I said, like for text generation model, the kind of explanations that I showed to you, that you can do, because essentially, forget about what is GPT-3 or like how it depends on the output. explanation approach depends on the outputs. It's a text generation model. So the way the embedding or like those kind of text generation model was explained, you can also be explained that. Or we can do an user study and ask like what kind of explanation people actually want. As I said, depending on the user. Like some practitioners, the ML practitioners, they may want to know something different. Like they may want to know maybe the importance of different layers in the GPT-3 architecture. So then in that case, the explanation will change. And if you want to know like why it has generated the particular test sequence, then.
So it's very much dependent on the application.
Yeah, it's very much dependent on the application. So this XAI tutorial is already there. You can check out, like they have a very good detailed tutorial. They have given tutorial in XAI, new rips, I guess. And so this is a very good tutorial. And they have also Hima has also a YouTube
She is
lecture.
at Boston University.
Harvard.
No, no harm.
Harvard. Yes, sir.
Thank you. Any other question? Okay. Let's thank us again. Yeah, thank you. So, Prachita, you are continuing on this one.
Yeah. I'm trying to do
So,
domain specific things.
we are thinking like maybe for cross language, there are some important explainability thing in a cross language. For example, if you are doing a missing translation, why have you come to this translation? So that's very important.
Yeah, so that's why I showed the initial
Right.
one of my presentation. So they didn't try for explanation because it was a 2015 or 13
Right.
model. But eventually the matrix shows that what is the influence of the previous input tokens, the alignment model in that. I think that kind of architecture is useful for
Yeah.
machine translation.
Like there are things like Puspakta was telling that you have this Indic languages, Hindi. So if you explain, you can figure out that corresponding words in Bengali, Hindi, these are all the same. I mean, they appear together. Or,
I mean, in translation model,
in translation model.
Yeah.
You can create a dictionary out of the translation model if you try to explain it.
yeah, I think, I mean, like it depends on like what you want to explain. One way people would like to know is like, suppose this was the input set.
Right.
Why the path token was generated? What is the
Exactly.
influence of the previous input? So that was the example. But apart from that, I think we can like someone can think of also other types of
Yes, you
explanation.
can say that attentions are somewhat explainable.
Yeah, some people have tried to use attention.
And but there is a debate like attentions are.
Yeah.
Oh, okay.
Yeah,
By definition.
Yeah.
yes. There is
Seems like we have plenty of time, so we can continue. I mean, lunch is supposed to be served at 1:30.
1:30, yeah.
So it's
No, but Prasita, you sit down.
Yeah.
If you want to have some water.
some explanations.
Yes, Rupendu, বোতলটা দাও। আচ্ছা, বোতল।
জলের ওষুধ কোথায়? রামপুরহাট।
Yeah, actually for cross language, it's pretty open. I mean, not much work has been done.
What is pretty good? Explanations.
Expansion.
What do you want to explain? Machine translation models.
No, say I want to do a cross language ad hoc retrieval, let's say.
Okay.
So I fire a
Yeah,
query.
one has tried that, like,
No,
yeah,
one has
why-
tried that. Why this document is at the top? So I want to fire a Bengali query and rank English documents.
yeah, because people have worked on transfer model, transfer learning things on
Yeah.
this one. So then we can say that what particular, so this is kind of related to that influence function thing.
Influence.
Concept of
Exactly.
influence function. That's-
So, but there are no papers on that.
No, I mean, I'm not aware of that.
No,
Which
I
particular-
haven't seen also.
Yeah. So which particular input instances of that language L1 influenced this kind of retrieval in this? I think
Okay.
that can be
That
one
can be
in.
done. Maybe, do we have a tracking fire on explainability?
We don't, but we are about to throw a track on machine translation, which requires amount of processing world.
But why not, can explainability sense?
This could be, this amount of track, we will give a this, the floor is open, why don't you?
But I am an old man. The other people have to think about it.
Who am I? The guy sitting beside you.
He is not old.
He is not old. He is working on some of these stuffs.
No, no.
Oh, this guy.
And of course, beside you.
I'm old.
No, no, it has nothing to do with old. I mean, yeah, so current Spark Jones wanted to come at the age of 90.
Then
Yeah, so that's a good, you can, I mean, because this cross-language experiment is completely open. Nobody has a track on it.
You want to explain the importance of terms in documents?
No, she has spoken about the evaluation methodology. So based on that, we can think of a track where you evaluate. So
You tell a ground truth for the document.
yeah, down to has to be created.
the grand rules I can create. I have some fun for that.
Actually, 2 days back, we were discussing about the tracks thing, the complexity of the tracks. So like, I'm just asking, like, won't it be too complex for the participants, like, because
No, they are standard tools
Bouquet
available.
of tracks. Reckon a bouquet of tracks, so as based on the complexity level or difficulty level.
Yeah.
People will pick one or two based on their what they can afford.
Yeah.
But we should design it. And maybe while designing, you can figure out that there may be an easy version of it, not so easy version of it and so on. So, but it's a work trying exercise.
Because see, another thing is when Fire started, everything, the track started, they are from scratch.
Yes.
Now we have all these libraries in GitHub. You can just, so that the climb is less.
And you can make it optional, right? So not everybody has to take participation in every. But have like
Anyway,
three or
we
four
can,
different-
let Mandata come in the panel, we can discuss. Evening panel.
It's already gone.
So apparently it's over.
It wasn't Friday, right? It was on steering
Apparently it's
committee.
over.
Yeah.
So basically, we solicit your advice and your suggestion here. Please go ahead. I mean, if
We have time, right? So we could have some discussion.
Yeah, okay.
If we have time, yeah.
You want to propose a track on cross-lingual explainability on cross-lingual?
So let us figure out that whether we have a track on, I mean, monolingual explainability of IR.
No, we don't have.
We don't have.
There has been no such track.
We have all those ad hoc track results available from early fire. Yes. For about 5-6 Indian languages.
Now, all one needs to do is to open up the relevant documents and then highlight that, okay, so maybe this part is.
Yeah, so the
important.
judgments are there.
There's some kind of sub-level.
Actually, during when the rail judge was done, this was part of the exercise, we did not note it down.
Yes.
Yes.
Yes, because at the time we were not aware.
But
that
there are
some-
collections which has got sub-document level information, like the INEX collections.
Yes.
They have this.
I
sub-
mean, even
passage
in
level.
the annotation, we can do something like the first evaluation approach that I was talking about.
Yeah, exactly. That
If the
can be
model
done.
is predicting that these are important terms and we remove those and the score drops drastically, obviously it is some kind of indication that. this is an-
Indication that.
So these can be captured in a track. I mean, we have all the past fire ad hoc tracks.
Ad hoc tracks are
All
there.
the hand judged and relevant judgments that we did, you remember.
Huh.
For at least 5 Indian languages.
5 Indian languages.
That includes Bangla, Hindi,
Huh.
I think Tamil, Gujarati, Marathi, yeah.
So we can, what Puchita is suggesting
And we can add
directly,
English on the top of it.
yeah, we
So
can run this approach, get the important thing, do a pulling on that, and then once again do a rail judge on
Sure, we
the.
can share these
Yeah.
stuffs, yeah, we can take that.
But do we need to do pulling because they already have the relevant documents, right? So.
No, what I mean to say is that you have the relevant document, you run this algorithm, external,
That is
pick up the top
something that we
words.
do. Yes, pulling is different too. But then pulling is going to take a longer time rather than reading a document and then highlighting
Okay.
the relevant chart. I think that will be easier. to do.
That will be easier, fine. But then do you have the manpower?
Yeah, manpower.
Oh, yeah, woman means default powerful, I mean.
Man is homo sapiens. Man is homo sapiens.
Now, okay, so anyway, don't digress. This, do you have the,
So we have to figure it out. So basically what we can do, currently I am running a funding on machine translation. Which
okay,
is essentially cross-lingual with all those neural machine translation.
so
models to
who are
compare.
tagging it? Who are doing the rail judge?
No, he is the captain of that whole.
Yeah, so,
thing.
so Captain.
So
you
we
can-
hired people from Gujarat, so we are, as per the language vertical wise, we are taking care of Gujarat.
Fine.
Now, we have our peers in for Bengali, for Tamil and for
No, but let us do it Gujarati.
all these friends.
Huh.
So we can collect those judgments.
And when they are doing the judgment, why not give them a tool to say why, and mark out some
So
sentences?
we have to create such an interface. So currently what we are in between is that we are trying to do machine translation between exotic languages. So say Gujarati to Chinese kind of.
Okay.
So we need human who are translating manually. Given Gujarati piece to Chinese piece or for that matter, whatever language source or target.
Right.
So now,
No, but
that
you are
is the
saying
interface we
that,
have currently. But we can update that interface that why you are translating to this or rather why you are picking this vocabulary to represent that vocabulary, something like that.
Actually, sir,
But you are talking about relevance, which is a different thing.
creating actually when once the translation is done, later on just creating the vocab, the exactness, because so when doing translation, actually for some languages which are not similar, especially the syntax actually completely varies. So for such tasks, like just creating a dictionary, like post translation, if they try to create a dictionary, like this is the parallel word of this in the other language. So even that could be an explanation, like when it comes to just a machine translation.
yeah, that's what I was also thinking, like create a dictionary, just an ad hoc dictionary.
But that's the cross-lingual.
Cross-lingual
Monolingual.
So you are talking about a monolingual explainability.
So let's start.
No,
with-
but I mean, we can try both.
You can try both.
Because the other one is I have to try because that's what I have been asked to.
Because for the
So you can
cross-lingual-
add this as a task to your project.
Yeah. If I can add this monolingual.
So for the cross-lingual thing, there are two components here, right? So one is the machine translation model or whatever, what translation model, and the other is the ad hoc retriever. So you could have neural models, right?
There are two models.
There are two separate models. And explanations should work on only one model, right? So that you cannot explain the whole two cascading of models at one time. That's not possible to do. Unless you have a joint model, it does it joint, right? So you could have a neural CLIL model, and then you could explain that model. Other than that, if there's two different models, then they have two different levels.
Yeah,
of
something
explanation.
similar.
No, then maybe you can start with monolingual list.
Yeah, monolingual is simple.
Monolingual is like it there, just you let me know what kind of annotation you require. And we need an interface.
I don't
for
require
that.
anything. I'm not a part of this.
No, supposedly, what we should do is that you have the ad hoc railjas for the previous
Right.
tires.
Yes.
Is it possible to give them the railjas, the relevant documents and tell them that why these are relevant?
Yes. Because the document repository is also.
Is there, so somebody just looks at the relevant document and
And then
then
write an explanation.
write an explanation. Or just highlight some words, why this is given. Just mark some words, that this is, because of these words, he has come to the top.
So I
This is some annotation based and as well as some, there can be some intrinsic also, like the automatic one,
Yes,
where you have the document and they just come up with this.
that is also possible. So that can even more easily be done.
In that case, we don't need any kind of-
You don't need any kind of annotation.
I will share you some sample.
তাহলে বসে থাকেন from
Who
Liverpool.
is the custodian of higher data?
Yeah. You can start it. So let us.
In this context, I have one query to Devashish and to both of you that we are planning to train a model, okay, where we have input two-scape document in a particular source language, okay, and output is a summary in a different language.
Cross-lingual summarization.
So that's a single neural one.
So he is from Bangladesh. He is working on that problem. Yasir Arafat.
I am the assistant professor, Department of Computer Science and Engineering, Joshua University of Science. Is the near about Kolkata.
Sorry.
Joshua is near to Kolkata.
Joshua is near to Kolkata. We can take a bus from here, right? Yes.
So he is working on a summarization model, cross-language
Something like that.
summarization.
Bengali and
Bengali.
You want to throw some light on the model? Like, what kind of modeling you are doing?
Just the Oracle one.
But he is creating a data set also. Annotating and creating
But is it like
from Joshua University.
Is it like one
Curious
joint model?
question. Do you have collections from Prothomalo? They are archive of last 10 years or something like that. Is it difficult and how difficult is that to get? Like we have something from Anandavaya. And these two technologies are different.
No, I have I had not the collection of all data, but I have some.
No, I'm asking how difficult is it?
Get the collection from Prothomalo.
I can share it, but
Can you check? Yes,
next time I will.
sure.
But then our Anandavaya is from 2001 to 2005, right?
Yeah, but actually they have all these archives. I once visited Prothomalo.
Okay.
The-
So Prothomalo should have that. Prothomalo should
Prothomalo
have.
should- they also have similar period. 1999 onwards, they have the digital stuff.
So we can get a bigger.
Only thing
bigger
they have a
collection.
proprietary font, which is Ekushe Bangla or something that you have to
But
write.
nowadays with all these available technologies, it would be
Ah,
quite
it's
easy
a
to transfer.
Unicode
that
and
to
that-
internet.
We have to
We are
start
talking
with
about
the-
like fire during initiation of fire, right? That was like 15 years back or even more.
Yeah, okay.
Then technology was not that mature. But now I think, dealing with these UTF-8 characters is like child's play.
So which was the young man. then.
Yeah, yeah.
You were also young.
I was a boy. I was a boy at that. And no.
Your class 9 additional was IR or something.
So do you have like two different models or only one joint model that you are trying to? For the cost?
No, he's building it.
He's building. So I think if there are two models, then.
But what we want is that, do you have some students in Joshua University who can annotate and create this?
Yeah, that would be a great help.
He is a teacher, so you can, yeah, you can have some students. So what we need is that we'll have an, say, English query.
Yeah.
And a Prothomalo collection, let's say, and then you translate and bring out the top documents, and then some students sit, look at the query, look at the document, and say it's relevant or not relevant. And then mark some words why she thinks it is relevant.
Yes, but I will do it manually.
And this has to be done manually. This is by definition manual.
Then I put this data in my model. Then
Train and build a model using this as a training data,
then again I validate.
and right.
Then I analyze the.
And like, so maybe we can proceed. We can give him the query set.
Fire query set.
Hmm.
That is available.
That is available.
Query set you can simply download from Fire data section in the Fire website.
And run that on Prothomalo.
Yes.
So you want to extend relevant judgments on. You want to
Prothomalo.
extend the collection.
And in that, so basically, we build a Prothomalo rel judge, and since we are doing it over again, we ask the annotator to mark the important words also, which will be useful for.
Okay. But we also have the relevance data for Anandavaya. So in those cases, we don't need to do the pooling and then do the document relevance. data.
So, okay, so that maybe they can do that directly on that.
Yeah, exactly. They're doing it on Prothomalo. So we can give them the relevance. documents
So we'll
for
give you
Anandavaya.
some English queries and the Anandavaya collection, Bengali. We have the top document, relevant documents,
We already know that.
already know that. So the annotators has to go through this document and mark some words and say that why this has been important. Yeah.
Words or phrases, whatever.
What's are this relevant?
That sounds like a plan.
So we'll follow. But we need some hands. to do
Yes.
this, and eyes there to do this.
Hands and eye.
Okay, that's a good plan. And then after this is ready, then we can contact Prachita and get
Meanwhile, I
Exact
will
definition and other
the documents for you.
so there will be people at Liverpool, students will be interested. Students at Liverpool will also be interested to work on this, or maybe you have your own resources. Right, so they can.
let's say. First step of building was to first work on creating the trust level.
That's what he said.
That is something that's what
We have to build a slide.
yes. So because prior research is not done like.
No.
This track, not participants, so we have got two dots. One is that you need to retrieve relevant documents, the other is you need to point out to specific phrases in the document. To explain, like, why is this, right? And then we already have the manually and.
So this is like ad hoc retrieval plus plus. Ad hoc retrieval plus X.
The plus sounds fine.
No, there has to be an X there. X for
Ad hoc
extension.
retrieval plus X. So the same ad hoc retrieval model that we ran in Fire. We in addition to that relevant judgment, we have to also give an explanation why it is relevant.
So it should be XAI here. Explainable
XAI.
ad hoc here. XAI.
So in addition to the same talks that continues, we add an additional talks of giving an explanation.
And then
Explanation
evaluation
in the
steps
form of
by
what?
Important words.
Important words.
what's the phrase?
So you have to rank the documents.
Mhm.
And for each of the document in the ranked list, you have to give a set of words and phrases.
Okay.
Why this is ranked.
And then there are two different dimensions for evaluation. One map, standard one.
One is the standard
Evaluation.
retrieval.
One is this, Jacquard or whatever overlap with this contour.
With
And
this
then-
count.
And then you can combine that with an export kind of, right?
And also the way Costa suggesting without the annotation that way also. You can.
Even the intrinsic fidelity as well.
Intrinsic fidelity.
Fidelity you can measure. So you have 3 scores. And then depending on that, you could like.
I think no one even have generated the explanation for IR, right?
No.
And the ground truth, right?
Nobody has done. So that's the value. That's the
Just a
value.
right.
That's the value.
Yeah, so two different ways of evaluation.
And that will get a lot of participation.
Hope so, yeah. And that may put participation from outside India also.
Outside India.
Yeah.
I can check with NIST and get the NIST WSJ documents, and we have
that already.
we have that, but we need the permission.
Okay.
So I can check with Ellen, and
Oh.
I can rope in Ellen also in this team,
Yes.
at least her consent. And
I think
Nicola
we'll get more participation if we do it on the trade documents, right?
Yeah, so I will try to.
And we can
put,
release it as Sigaya resources.
Ellen was there in the steering committee.
Yeah.
So Ellen was there, Nicola was there. So we'll pull.
So let's start with that. So if we can do this, and we can release that as a Sigaya resource as well. We can send a paper to the resource track of Sigaya.
Okay,
That will publicize the data set.
okay.
And then we can go for the track, right? So a track starts at around like summertime in Wire or what. So before that, if we can get this out in Sigaya, we can publicize
So
the
Sigaya deadlines are too short.
resource paper should be end of January.
And this
Yeah, I mean,
is.
in law, 1 month.
Let's target next Fire, then we'll publish.
No, but
I wish to target
will
this
talk with you about that.
Why don't you target this one? But maybe as a Sigaya resource paper, maybe the next. one.
Okay.
Maybe the next one. So let us meet sometime to formulate the annotation policy.
Yes.
But even this proposal itself can be a Sigaya paper, right? I mean, evaluating systems.
Proposal is.
No, proposal is not. No, evaluation is already known.
Yeah.
Evaluation is common.
Perspective paper. It can be good
No,
perspective.
what Devashish is telling us interesting, basically, if we can propose evaluation, you have to pose it accordingly. That don't just.
That is common. This is common.
This is common.
No, there are two things to it. One is the fidelity thing, right?
Right.
The other is the.
Jacquard coefficient.
Yeah, these are common. These are common things, evaluations,
Yes,
evaluating.
but ranking systems based on this combination of these two.
Oh,
is
that's
something that people have
straightforward.
done.
That's why it is straightforward. If you look at.
People publish more straightforward work than this. In
No, we don't, we not do that. We not do that.
Sora only publishes when it comes to something like Okapi.
It's all about selling your work, right? I mean.
These are like quite straightforward. Why
Okay,
don't
we'll
we?
take a shot.
You need to convince the customer that this is new.
You don't want the point of research. Like, you.
No, but more importantly, let's formulate the tagging policy. Tagging policy, then we can write a paper, Devashish can take care, write the paper.
Like Like if you work with the trade documents, like I'm prepared to annotate it myself. I can dedicate like 2 hours of my time.
Okay, let me get back to you on
If
this.
that-
So once we get the policy, we need some annotators
Yes, annotators per language.
per language.
No,
So
language is-
let us start with English, WSJ.
That's okay, but also why not add Indian language from the
Yeah, I think
beginning?
that is an interesting thing, but we
That
can
would
start
give
with.
yeah. Everything started with English.
All right.
No, fire trap we are definitely going for, and then for fire trap we are using the fire collection.
Yeah, okay, so fire collection we should use.
Okay, let's
So
work.
I will get some Gujarati annotators.
Hmm.
If you can get some Bengali annotators.
You can get some English.
And.
So what we'll give you, we'll give you a query and I say Anandabajar collection, the top ranked documents according to that query, and then the annotators have to look at the documents and say, because of these words, these are rank high.
So I try to find some.
Mom annotator, so good.
Sharan,
So we'll
what
explain you the
language
policy,
language
you can explain it. the policy.
But there should be some limitation on tagging, right? So I could highlight the entire paragraph.
Yeah, all those we have to set up in the
Tamil,
policy.
Okay. So
Yeah, Tamil you can do.
Tamil you can, so Tamil.
Hindi you need
Gujarati,
annotators. You need what annotators for the annotators? I can do it.
So Tamil.
Hindi.
Oh, Hindi. Bhargav is here,
Yeah.
So there are Hindi takers,
Very good.
and Saurabh can take care of Chinese.
I think it will be also an interesting observation, right, for the languages which are similar, how the.
Exactly,
expressions are
that's
also,
what I was thinking. Are they similar also?
Similar. I mean, like, I was thinking of these two different Bengal, I don't know whether the different Bengali language that was like Bangladesh and India. Yeah, because we have two different versions of Bengali. I don't know whether there are any rituals or something. How these, I mean, like, so there is this famous paper where people are talking about this disagreement about the explanations and all. So since these two languages are very close, so how that explanations are, like, they are also correlating or not, how much correlation is there? I think these are also interesting observations.
Very much interesting, and there is slightly different.
Yeah, I mean, ideally it should happen that the same word should be kind of like the same word, different version should be presented in it. But maybe we'll see that the native speakers are picking different kind of words for explaining that word.
Which are,
That will be nice.
then Bengali is fairly similar, I believe, but spoken dialect is.
No.
significantly
What you said is different.
Slightly different.
Some exceptions.
For example, you Bengali, we say body, they say basa.
Some words are different. That I-
No, not only words, application of words.
Phrases are
Many
different.
Very different. I
Hidden
agree.
version.
Into the two version of Bengali. Suppose if it is calling someone over phone, in this part, people will say ki আমি ফোন করবো।
Fondish.
In that part, phone দেবে।
Fondish.
In Bangladesh, the standard written version is to Bangla. But here it's different.
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 The usages are also very different, and the meanings are also very different. The way you are applying it.
Yeah, all the valid words from Bangladesh are also valid words, but their usages are
And
different.
what level, yes.
So all
Beyond what
similarly,
level,
yes. All the West Bengal words are also valid Bangladesh
So they
words.
are Bengali.
They are all Bengali, but the usage is different.
So that is an interesting study. I mean, the
Yeah, and I
distribution
think
was.
the motivation over here is like, if we see that there is significant number of overlap, then we can say that for if we have annotation for one language, we
Can we
use
use it?
from-
Excellent.
Actually,
So I'll put you in touch with Projeta. You can go ahead with that.
I think already such study has been done for Spanish and Catalan.
yes, something like that.
Catalan
Very
language.
precise. Yeah, like, in fact, I think Catalan is the dialect of.
Yeah, Catalan
Spanish.
is rather.
But they don't accept that. If you ask a
If you go to Barcelona and say this.
I just go and what's
But I
still respect your life there.
But I didn't understand, like, how did they allow to conduct a WMT track on Spanish to Catalan translation?
So we can also plan something
They somehow.
from East Bengal language to.
That's what I was thinking.
What is the border?
Catalan is not really a dialect of Spanish. I think it has got like.
Because actually for machine translation track, they achieved a blue score of 83, which is not or even Hindi to Gujarati.
Yeah, it actually does prove that it's that. right?
Yeah, yes, that's what I to interpret it.
It kind of backfired. Organizers, they wanted to do something else.
Yeah, so this, but I think important if you get the Prothomalo collection, that is it.
Yeah, that will give us.
If you have some contact in Prothomalo,
I will try to contact him to collect the archive.
select the archive. And then they have their own font that your students
will
can
take
work
care,
and
yeah.
work on the font.
These days they are using Unicode.
Unicode there, so
When
no
I
problem.
visited them way back in 2009.
They are
and that
using
time it
some
was
coding.
actually Bangla font and all those things.
Okay.
There was some.
Now it must be
senior
Unicode.
fellow, Mustafa Jabbar, you heard him?
Yeah. I know him.
Acha. So he took me there in the Bangla Academy and then he explained that these are the issues that I asked that why it's still not in Unicode. So he said that, I mean, this is the first way where we are at least getting digital. That was way back in 2009.
Maybe if you know most about her,
And he seems little close to the
then
government.
you can connect.
I mean,
He is also from the government. He is close to the government. You have somebody from the government parliament, no? Bangladesh parliament
Yeah, yeah.
in your group.
Ibrahim.
Ibrahim is there. He is
Okay.
a member of the parliament.
Great.
So they are a group who has come to IIT Kharagpur for a
He is
course.
the programmer of.
Yeah, I know.
He is the programmer of parliament. Okay.
Okay. I know.
So yeah, maybe then we can get the Prothomalo collection and. Then Prasinda, I'll connect him with you also. If you can tell him a bit about the.
I think we have.
Annotation, then he can ask his students to do the.
Sure.
Okay. And this XAI, then let us meet once more.
Let's develop, yeah.
Meet once more, maybe online, and then get the annotation policy ready. That, as you are saying, that you think of what can be the policy. Maybe you can prepare a draft of the policy and present us.
Yes. That's better.
Prepare a draft policy and present us. Then we will get the annotators and start the annotation.
Sounds like a plan, Devashish. Job.
Now we are hungry.
Now let's go.
Job.
Huh?
Job.
It's a job.
Graham Glasgow.
Hello. Hello. Hello, Graham, are you here?
Yes.
Maybe right to him.
I'm not in. No. Okay, can you try once now? Not able to.
Yeah, hello, good morning.
Right.
Okay.
Okay, I think you can now try to share your screen. Yes. Okay.
You see that okay?
Yeah. It's visible. Okay, we can start now.
Okay, thank you for inviting me to give the presentation. I hope the conference is going well. Looks like there's a good audience there, good turnout. My name's Graham MacDonald. I'm a lecturer at the University of Glasgow. One of my main sort of research interests is how do we develop fair ranking strategies that can provide a sort of fair exposure to particular societal groups or authors of documents, for example. I've been an organizer in the TREC Fair Ranking track for the last couple of years. The work that I will present just now was published in the end of last year, and it's work sort of based on the first couple of years of the Fair Ranking track, TREC Fair Ranking track. And the title of the talk is Search Results Diversification for Effective Fair Ranking in Academic Search. So a couple of things to pick apart. First, search results diversification. I'm sure a lot of you will be sort of very familiar with this. I'll say a wee bit about it as we go along. And effective fair ranking in academic search. So what do we mean by fair ranking? Okay, so traditionally, an information retrieval evaluation, the objective of the IR system has been to maximize the relevance of the results from the perspective of the user. So for a particular query, a search engine will return a ranked list of results, and traditionally this ranking has been optimized only for relevance to the user's information need. However, if you optimize only for relevance, then this can have some undesirable side effects potentially. So if you think of different societal groups or different sort of authors or things that documents talk about, so when you've got equally relevant documents and the system is generating a ranking based on relevance, then if there's a set of documents which are all relevant to the user's query, you have to split ties, and that's done by predicting their estimated relevance. It means that some of the documents have to be placed higher in the ranked results list than other equally relevant documents. So in the literature, one of the sort of obvious examples that are used to sort of explain this is the notion of, if you do a query for, say, CEOs, if you're looking for CEOs of a company, and if all of the male CEOs are placed at the top of the ranking, then it's less likely that female CEOs will actually be exposed to the users when they're looking for relevant results. And obviously this is unfair on that particular societal group. In this example, we're talking about gender as the sort of fairness characteristic. So there's been a lot of work recently that sort of looked into how, different strategies, how can we actually develop ranking strategies that are fair and don't discriminate against particular societal groups. And obviously these societal groups are potentially infinite, the number of groups that there could be. So, there's a lot of open questions as to, when you're thinking about these kind of systems, do you select particular groups that you're interested in being fair to? And if you do select particular groups, are you automatically sort of being unfair to other groups that you're not potentially considering when you're designing your system or your optimization functions? So there's lots of sort of open questions around this, which hopefully I'll get a bit of time to discuss at the end. But what we did in this work is, like, we realized that there's some parallels between search results diversification and this notion of almost like diversifying a ranking, so that you're diversifying over these particular societal groups that you're wanting to be fair to, you're aiming to be fair to. So that's the basic premise of the presentation. The outline, I'll talk a wee bit about academic search, because this work is actually, it's developed within the context of academic search. The things that we're interested in about fair rankings and exposure to particular groups are, they're uniform to whatever context you're actually investigating. But within this work, we're obviously doing it within the context of the first couple of years of the fair ranking track, and the collection and stuff that we're using was academic search. So I'll talk a wee bit about the task at first, and then I'll talk a wee bit about how we cast the fair ranking problem as a search results diversification task. And then we'll go on to talk about the methodology, briefly sort of talk about the results and some conclusions, and hopefully get a chance to talk about some open questions. So as I said at the start, this work was actually published towards the end of last year in the Information Retrieval Journal. The title is Search Results Diversification for Effective Fair Ranking in Academic Search. And it was the work was done with my colleagues, Craig MacDonald and Iad Unis, who are both from the University of Glasgow as well. Okay, so what is the fair ranking task in academic search? Okay, so I'm sure you're all aware of these search engines that we use to find academic works. Obviously, Google Scholar, Semantic Scholar, Archive, Zeta Alpha, and newer ones as well. And we use these products probably every day in our lives, you know, and often we're looking for a particular article in which it's a known item search, or you're looking for a particular paper. But often, you know, when you go to investigate a field at first, you're looking for a sort of breadth first search where you're wanting to get an overview of the work that exists and the important or salient work to whatever domain it is that you're actually investigating. They typically follow a very sort of straightforward 10 blue links presentation strategy. So obviously in the first page, you're only going to get maybe sort of 5 to 10 results, and these are typically the results that the user will see and will assume to be the most relevant. So they're the ones that are going to get the most exposure to the users, and they're more likely to get clicked, and the user is less likely to move on to sort of secondary pages. Okay, so we're in the context of fair ranking, and we want to provide whatever these groups are that we define. We want to provide them a fair exposure, and we're working within this context of, users are used to these information retrieval sort of interfaces, and they work within them. So let's just take a quick example here. We have this query, positive psychology and academic performance. So this might be a sort of a typical query that you might put in as your initial search term when you're starting to review this field of work. So a typical search engine will rank these documents based on their estimated relevance or their predicted relevance. So here we see an example with 4 documents which are ranked in descending order from what the system thinks is the most relevant to the least relevant. The most user models that we work with within information retrieval assume that the user start at the top of the ranking and work their way down the ranking, stopping with some probability when they reach a document that they think is relevant. So you're going to start at the top, you're going to work down, and then when you find something's relevant, you're likely to stop with some probability, or you might move on to find something else. Okay, so here we see that these documents are they're predicted to have an estimated relevance, but and with the user moving down from the top of the ranking, the exposure that the documents are actually getting to for the user decreases as we go down the ranking. So, there's different ways of measuring what this exposure is. One sort of common or way of doing it is just 1 over the log of the position of the document in the ranking. So this is like the position bias model of sort of NDCG and well-known information retrieval metrics. So here, in this example, all of these documents are actually relevant to the user's information need. It's just that they've been ranked by the predicted relevance, the system's predicted relevance. So here we see that there's 2 different groups of authors. Let's just, for simplicity's sake, say male and female. Say the light blue group is one particular group, and the dark blue group is another group. Now here you see that obviously both of the documents from the light blue group appeared at the top of the ranking, while both of the documents from the darker blue group appear lower down the ranking. So obviously this means that the darker blue group is less likely to be, they get less exposure, they're less likely to be seen and clicked by the user. Okay, so how can we start to think about how we can address this unfairness in this single ranking? So here we see obviously that just the numbers, although the estimated relevance is quite similar, the exposure that the groups get is vastly different, you know. So the light blue group is actually getting roughly twice as much exposure to the dark blue group. However, so one of the sort of characteristics of search that we can use to hopefully try and like correct for this bias is that queries are often repeated multiple times. So that could be either you repeating the query or multiple people repeating the query. So that means that we can generate different rankings for each of these queries. And when we generate a different ranking, we can permute the ranking slightly so that when we evaluate fairness over the whole set of rankings, then we can compensate for this underexposure in the initial ranking. So if we evaluate the exposure over all 4 of the rankings, we see that now both of the groups have an equal exposure. So we could say that this strategy is fairer for the information producers. It provides them a fairer exposure to the users of the system. And that's generally what we're aiming to do in the fair ranking track or task. We're wanting to generate a set of rankings for a particular query so that when we evaluate the exposure that the different groups get over this set of rankings, we want it to be fair or proportionate to the true relevance of the documents. However, in this example, we're almost like assuming that we know what these groups are. However, in practice, it's often the case that you don't really know, either you don't know what the groups are that you're really trying to be fair to, or you know, there's so many different groups, like I said at the start, it's almost infinite the way that you can define these groups. So you've got a question as to, do we optimize for particular groups, and in which case we may be sort of disadvantaging other groups, or do we assume that we don't know the groups and we try and come up with a sort of generalizable strategy that can be generally produce fairer rankings. So in this work, we do not know what these groups are when we're actually developing the system. You know, we have to try and come up with strategies that might in the end provide a fairer ranking for the groups. Okay, so we're aiming to provide, we want it to be fair to members of subgroups of unknown groups. So therefore we have to sort of make a reasonable sort of first attempt at thinking what would be reasonable groups we want to be fair to. So in this work, we thought, well, in academic search, maybe you're wanting to be fair to early career researchers as opposed to, well, as well as professional researchers. So when you're at the start of your career, you're wanting to get exposure to the users. So there's characteristics of the document that we could potentially use to uncover these sort of latent author groups. For example, the number of citations that particular authors have. So if obviously if you're at the start of the career, you're likely to have less citations than you know, more experienced professional researchers. So we can define fairness groups based on such characteristics and use these as a proxy for what we're really wanting to try and be fair to. In this work, we focus on 3 main ways of sort of modeling the groups that we might be interested in being fair to. So the author's experience, i.e. early career versus professional, the publication venues that a particular document is published in, and the main topics that are discussed within the topic. So I'll go into these in a wee bit more detail, but we're using these as a sort of proxy to think, you know, if we're wanting to be generally fair, these are sort of things that we can first try to be fair to, and then we can find out when we evaluated how fair we were in practice. Okay, so the overall, sorry, so how do we go about casting the fair ranking task as a search results diversification problem. Okay, so search results diversification, like I said, I'm sure most of you are very familiar with it, but just in case you're not, search results diversification, there's a huge body of work that's been looked into for many years. And the sort of main premise of it is when you have an ambiguous query and you don't have enough context within the search terms to know which sense of the term of the query the user is actually interested in. For example, if the user enters the query Java, you don't know whether it's the island Java, the programming language Java, or the coffee Java. So you would diversify the rankings to try and make sure that some of your results cover the island, some of the results cover the coffee, and some of your results cover the programming language. And the aim is you're trying to diversify so that you meet the user's needs. In this case, we're trying to diversify so that all of the different groups that we're wanting to be fair to appear in the ranking. So the basic process is it's laid out in the slide here. First of all, we want to score the documents for relevance. As we've been seeing so far, we get the relevance focused ranking. Then we want to extract our fairness characteristics for the top K documents. These characteristics are the proxies that we've been discussing so far, for example, number of citations. We want to represent the document based on these sort of fairness characteristics, and then we want to re-rank the documents based on these characteristics. And we want to generate a set of rankings where when we evaluate over the set of rankings, the overall fairness of exposure for each of the groups is closer to the overall relevance of the documents for that group. So when we're using diversification, we look at two different families of diversification: implicit and explicit diversification. And each of these approaches, they have a trade-off factor in it, a lambda, where we can sort of trade off between relevance and diversification. And that's the main sort of tool that we use to be able to sort of generate this set of rankings. You want to vary this lambda parameter as you're producing different rankings, so that each of the rankings has a sort of a slightly different amount of focus put on fairness compared to relevance. Okay, so we evaluate 3 approaches for generating fairness groups and 3 search results diversification approaches, which are from the 2 different families, either explicit or implicit diversification. Okay, so what's the first author? The first assumed fairness group that we evaluate is author experience. So this is the one that I've been using in this sort of example. Want to provide a fair exposure to authors that are at different stages of their career. So early career researchers versus highly experienced researchers. So we use the citation counts of documents of the document authors as a proxy for the author's experience. So here in this little example, we see this document has 3 authors, and basically we go out and we look at the rest of the citations within the collection, and we just count the author citations. So here for this collection, there's 8 authors in the collection. This document has 3 authors. The first author has 7 citations. The second has 5, and the third has 8. And here you just see it. This simple representation allows us to have a representation of the fairness group that we're interested in. So like early career versus experienced, but we don't actually have to define the boundaries. We don't have to decide how many citations does an early career researcher have compared to a sort of more experienced one. You know, the system itself can work out the boundaries within these categories. So we don't need to define the subgroups. We can let the system itself actually work these out. Okay, so the second group that we're interested in, I want to provide a fair exposure to papers that are published in venues that might often be underrepresented in the search results. So we really were wanting to sort of surface documents from smaller or lesser known venues. Now, obviously, we all know, you know, like ACM publications and stuff like that, but obviously, you know, publications through FIRE or TREC or these potentially smaller venues, you know, deserve to sort of get the exposure as well, you know, if they're relevant documents. So, you know, realistically, all we do is we just sort of, for every document, we just go and we look and see what other venues this document is published in. And we just create a one-hot encoding representation, which says how many, for each venue, we want to know how much it sort of is known by the community. So how many other, for every venue that a document is published in, that venue is represented by the number of publications that that venue has. So again, it's a very simple strategy, but it allows a representation that we can then allow the diversification model to diversify over these different venues. And the third fairness group that we're interested in is a sort of topical grouping. So often particular authors focus on particular topics of their interest, but within those particular topics, there's also sort of subtopics that might get less exposure. So we just want to ensure that even sort of slightly less well-known subtopics of a particular topic are also getting a chance to be seen by the authors. So we just use standard LDA topic modeling to identify the topics that are discussed in the collection. And so again, it's the exact same sort of representation. We want obviously a uniform representation so that we can you know, make up as many of these different assumed fairness groups as possible and just feed them into the diversification strategy. So here, obviously, in this example, we have 5 topics, and each document is represented by the top 3 topics and how much that topic is discussed within the document. And again, you know, we can just feed this straight into the diversification strategy. Okay, so first diversification approach is implicit maximal marginal relevance. And here you see the formula for MMR. The thing that's of interest here is this sort of fair sim similarity function. I'm sure many of you might be familiar with MMR, but you have to define a similarity function that says how similar or dissimilar a document is to the other documents in the collection, because you want to include documents that are dissimilar in your ranking. So we just define the similarity function as the absolute difference in the scores of non-zero indices in the document representations. So that's why, you know, it's important that we just have this simple sort of vector representation representing the documents. Okay, and the second approaches are, or second family is explicit search results diversification. We evaluate 2 of these well-known approaches from the literature. Firstly, XQuad. It generates a set of subqueries to represent the different aspects of a query. So this is the key difference between implicit and explicit. And explicit, the aspects or the things that you want to diversify over are explicitly represented in some form. And then the last approach is PM2, and it's a proportional representation approach. It basically says that there's a certain number of places available in the ranking, and the number of places that are allocated to a particular group should be proportional to the relevance of that group. So I'm not going to go into in any more details than that. There's lots of details in the paper, obviously, but hopefully you're quite familiar with these approaches. So just to sort of put it all together, I just thought I'd give a sort of simple example of what this means in practice, with the example using the author experience and X squad as the diversification approach. So firstly, we generate the relevance optimized ranking. And here we see in the ranking that each of the documents has a different number of authors and different authors, but the red author is dominating the top of this ranking. So, if this was to be repeated deterministically every time the query was entered into the search engine, this unfairness for, the dark green author maybe would be accumulated over time. So we want to generate this set of rankings, and we want to have them diversified so that it's fair overall. X squad, it has this sort of simple mixture model where it's relevance plus lambda times the coverage and novelty, and we can make use of this coverage and novelty aspects in our diversification to make it fairer. So in practice, obviously, it's a mixture model. It does this process together, but really what it's doing, it's first promoting documents that are authored at different stages in their career, and then it's promoting authors that are not represented by already represented in the higher ranked documents. And this is the novelty part of it. So the coverage says you're wanting to cover as many stages of the career as possible in the top ranked documents, and then you're wanting to have novelty in there too. So you want to have authors which don't currently appear in the top ranked documents will get promoted to be there. Okay, so I'll quickly go through the sort of experimental setup and the results. So we've got three main research questions that we're interested in. Firstly, is leveraging search results diversification as a fairness component effective for generating fair rankings? Secondly, which of these families of search results diversification, i.e. explicit or implicit, is most effective as a fairness component? And thirdly, does diversifying over multiple assumed fairness groups result in increased fairness? So remember, we don't know what the we don't know what it is we're actually trying to be fair to. There's lots of potential assumed fairness groups. So, are you better off just getting as many as possible, and does this result in it being more fair over time? Okay, so we've already introduced the assumed fairness groups, the author experience, journal exposure, and the topical grouping. So in the results, these are denoted by subscripts A, J, and T, and we evaluate all combinations of these different assumed fairness groups. So we use the 2019 and 2020 collections from the TREC Fair Ranking Track. Both of the collections have the same 7,903 academic papers or paper abstracts, but they have different queries and relevant judgments. So 2019 has 635 queries and 2020 has 200 queries. So both collections have ground truth judgments of two fairness groups, so high versus low H index and low versus high IMF economic levels. So remember, we don't know this ground truth when we're developing our system. This is when you're evaluating fairness, it's subjective for whoever is like sort of viewing the results and who has a claim to be fair to. So you don't necessarily know how it's going to be evaluated when you're developing the system. As our metrics, we use disparate treatment ratio and disparate impact ratio. These are sort of well-known fairness metrics from the literature. I'm not going to go into them in lots of detail, but there's plenty of details in the paper if you're interested. But the one thing that's like sort of notable about the metrics, that a value of 1 shows that both of the subgroups are getting a proportionate exposure and impact with respect to their overall relevance of the group. So if it goes either side of 1, you know that one group is getting a sort of disproportional exposure compared to the other. Okay, so here, big, huge table of results. I'm not going to go through the results. I'm just wanting to sort of highlight a couple of quick trends. Okay, so firstly, here in the top section of the table these are all the different combinations of these assumed fairness groups. So all these approaches have a fairness component to them. And we've got single groupings at the top, we've got paired groupings, and then we've got all three, where we use all three, obviously for each of the diversification strategies. At the bottom, we have our baselines, which are firstly DPH, which is a relevance only component. So it's optimized only for relevance. And then we have a random component as well, just to see how we compare. And hopefully we do better than random. And hopefully we're doing better than the DPH as well in terms of fairness, because that's the whole objective. Okay, so for research question 1, is leveraging search results diversification as a fairness component effective for generating fair rankings? So on both of the data sets for all of the metrics, the best performing approaches in terms of fairness are diversification approaches. So this gives us some sort of confidence that diversification can be used. However, you know, as you see, there's quite a few red lines here. There's no particular approach that performs best on for each of the assumed fairness groups, or for each metric, or for each collection, you know. But in general, diversification is doing its job. There's still a bit of work to go to find out how you would actually use it in practice, but it's certainly a good sort of indicator that it's doing something useful to generate fair rankings. Okay, research question 2. Which of the families of search results diversification, explicit versus implicit, is most effective as a fairness component? So 5 out of the 6 best performing approaches are explicit diversification approaches. So here we see that we have X squad is best 4 times, and PM2 is best 1 time. So this really shows that by explicitly sort of integrating these assumed fairness groups, the diversification strategy seems to have more to work with and can produce a better sort of approximation of what it's trying to be fair to. And then lastly, does diversifying over multiple assumed fairness groups increase fairness? So again, we can look at the same results again, and we can see that all of the best approaches are either single or paired groups. So in fact, just adding more assumed fairness groups and trying to diversify over many, many more groups doesn't seem to be the way to go. And in fact, in the last year of the fair ranking track, we actually looked at sort of intersectionality fairness and found that it's actually a really, really tough problem. So there's a lot of work to be done to fully investigate that. So in conclusion, we propose to cast the task of providing a fair exposure to unknown protected groups of authors as a search results diversification task. We found that leveraging adequately tailored search results diversification can be effective for generating fair rankings. Explicit search results diversification seemed to perform better than implicit, and almost counterintuitively, maybe adding more assumed fairness groups doesn't necessarily lead to improving the sort of generalizability or fairness of the approaches. So there are similarities between fairness and diversification, and these can be leveraged, but there is still quite a bit of work to be done. There's a few sort of open questions still relating to this work and more generally. So, for example, is it appropriate to assume that you know the fairness groups in advance? What's the best way of evaluating these approaches? You have to assume that there's a right amount of exposure that the group should get, and how do you decide what that is? And obviously this notion of intersectionality, if you're being fair to one or two or three particular groups, does that automatically mean that you're well, forgetting about the other groups or being less fair to the other groups? And that's it. Thanks for listening to my talk. I hope that was informative or interesting in some way, and happy to take some questions.
Thanks, Graham. Questions? I have some questions for you.
Excellent.
Can you hear me all right?
Just
Oh, yes.
speak up.
Can you hear me all right now?
Yeah, that's a bit better. Yeah.
Okay. So, yeah, I mean, I was a bit confused about when you say that you want to generate multiple rankings, right? For one query, you are taking into account different permutations of the rankings of documents. Now, I wonder why is that? Because the output of the system is just one rank list, right? And we want to evaluate like how good or how fair is that particular order of the documents. So why would you take into account all these different orderings that's possible?
So if I caught you correctly, you're saying like why produce the set of rankings you would expect to be fair over a single ranking? Yes.
Yes.
Okay, so depending on how you define fairness and what your objective is, it could be possible to be completely fair over one ranking. But I mean, like in the example, if you've got if you've got a set of documents which are relevant to the user, so they're equally relevant. Relevance is a binary notion. It could be, you could have graded relevance or whatever, but assuming that we've got binary relevance and it's either relevant to the user or it's not, you have to rank documents by the system's predicted relevance. Yeah. And the majority of user models assume that you're going to start at the top of the ranking and work your way down until you find something relevant. Now, if you've got maybe 20 documents which are actually relevant to the user, the likelihood of the user reaching that 20th document in the ranking is much lower than reaching maybe the top or second or fifth document. So that's what you're trying to correct for. It's like you're wanting to give this relevant document that appears at rank 20 in your first ranking, you're wanting to give it an equal opportunity to get seen by a user. And obviously this repeated queries, this could be one person repeating the query over a period of time, or it could be like, all different users. So if let's just say the room that you're in at the moment, if everyone was to enter the same query and starting their search, If the results that were provided to everyone in the room were diversified to ensure that the different groups of information producers each got a chance at being at the top of the ranking, throughout that room, the exposure that the groups would have got would have been fairer than if everyone had got the same ranking, then everyone would have got more likelihood to have stopped at the top ranked documents. And those equally relevant documents that appeared at the lower ranks would have been missed. No one would have actually seen them. So that's unfair on the information producers that are producing relevant documents, but for some reason in that one single ranking, because you have to split ties, it ends up at the bottom of the ranking. Does that make it a bit clearer?
Yeah, I mean, I can understand the motivation, but what I'm struggling to find is like, okay, so what is the output of the system? So the output of the system is one single rank list, right? Now, let's say the system is not fair. So in that case, the algorithm, whatever it is, let's say BM25 or LM or whatever. So that gives you one rank list. Now that may not be fair, depending on the attributes, let's say each index or the author professional experience or something. So let's say the top 5 is not fair because, you know, it retrieves most of the relevant documents it retrieves, you know, it has got senior authors in there. So that's not fair. But then we want to rectify that situation, right? So we want to come up with a method that re-ranks the BM25 results and then gives a fairer rank list, where the top 5 comprises of authors that have less experience. So that's what I'm struggling to understand. So what is the output of the system? Is that one single corrected rank list, or is that a probability distribution over multiple rank lists that are all fair?
It's a probability distribution over ranked lists, where if you evaluate the fairness over all of the lists, then it's the amount of exposure is relative to the true relevance of the documents, as opposed to the predicted relevance from the system.
Right.
So, you know, like any IR system that we use, as a user, when you go to the system, you will do your search and you will get one ranked list returned. But as a system, it knows that this queries are getting repeated multiple times, and the same information need is getting addressed for multiple people or multiple times, you know, so it can correct for any potential underexposure of particular groups by diversifying over the set of results that it produces.
That makes sense. Okay, other questions from the room?
So just one more question. So in the ranking formula, you are using a lambda parameter to decide on the trade-off between the relevance as well as the fairness, right?
Yep.
So my question is like, why don't we go for some optimization technique, like first of scoring the documents with that, which is the objective function, with subjected to some constraints which actually restrict the search results based on the other novelty or other H index parameters. So why don't we go for such an approach? Like, is there any challenge in that approach, or is it the customizability is missing in that?
I think there are approaches in the literature which are constraint-based approaches, and they work if you know what it is that you're optimizing for. So you have to know the constraints that you're optimizing for, and if that's the case, then it's just a straight up like dual optimization problem or something like that, you know, where you're optimizing for relevance and fairness, and you know what the fairness constraints are. So there are approaches in the literature, and certainly other works have addressed it from that point of view. I think so the difference that we were sort of trying to investigate here was this notion of everyone's got a sort of claim, as all different groups in society have some sort of claim to fairness. They've got some right to say that we deserve a fair exposure within search results lists. And the number of groups that you could define in those senses are potentially infinite, you know. So as a system engineer, like, what is the best approach to take to try and do the best that you can to develop some sort of generalizable approach that in general can be fair to any particular definition of groups? So you don't know the groups at first. You know, when you're actually defining the system, you don't necessarily know the groups, and you want an approach which can be generalizable in the sense that you can define these groups any way you want, and you can put them into your algorithm, and your algorithm will know how to work with it. So the lambda parameter is actually, in this case, just it's a sort of side effect of the diversification approaches. On their own, the diversification approaches are deterministic, you know. So the reason that we went for search results diversification is just purely because there's a clear sort of similarity in some senses in the fact that you're diversifying the ranking. With search results diversification, you're diversifying for the user to meet the user's need. When you're casting it as a fair ranking task, you're diversifying to meet the needs of the information producers. So there's a difference there, but there is some similarities in this notion that you're actually wanting to sort of diversify this ranking. So that was our basic premise of our starting point, to say, well, let's see how these off-the-shelf approaches work in practice. But in off-the-shelf diversification approaches are actually deterministic. So whenever you enter a query, you will get the same ranking, you know? So without doing this varying of the lambda parameter, this is how we generate the variation over the rankings, or the distribution over the rankings within this set. So it's purely just a sort of side effect or characteristic of search results diversification. And I'm by no means saying that it's the best way to approach it or anything like that. You know, there's certainly much more interesting and intuitive ways that you can sort of develop a sort of generalizable fair ranking strategy without necessarily knowing the constraints that you're wanting to optimize over, you know. Does that answer your question?
Yeah.
Good.
Okay, I have a question. Isn't like fairness a very subjective issue over here? Like fairness for one set of ranked list with respect to one person is fair, but with respect to another person, it is unfair.
Yes, certainly. Aye. And like I say, this is a very open question. You know, it's in the fair ranking track this year, that's what we focus specifically on, this notion of intersectionality fairness. And we gave participants, I think it was 8 or 9 different fairness groups to try and optimize over. But then when you look at the combinations of the interrelations between these groups, we ended up with something like 11 million different subgroups of who you could potentially be fair to. And we gave, you know, we didn't stipulate explicitly to participants that you have to optimize for all of them. We said you could do whatever you want, but the main metric was going to be optimizing over all of these 8 groups. So obviously when we rank the systems over the 8 groups, we get their official metric. But as an additional evaluation, we took these different subsets of these potential groups and saw what sort of effect does it have on the ranking of the system. So in other words, if you're trying to be fair to a particular subgroup, does that automatically mean that you're going to be unfair to another group? Or, you know, if you decide to evaluate it over a different group, does it mean that it changes the outcome? And what we found was that, surprisingly, for a single ranking, it didn't actually change things too much. The optimum group or the best performing group over all of the rankings was actually best when we looked at the individual subsets as well. But for the set of rankings, for this repeated queries and you know, when you're optimizing over a distribution, we found that, you know, it had quite an impact in the rankings of the systems, depending on the different subsets of these fairness groups that you evaluated on. So certainly there's a large open question there about you know, what's the most appropriate strategy to take. You know, do you specify a particular group and you optimize towards it, or do you try to be general? And in either case, what's the knock-on effects to other groups within society? So yeah, it's a very good point, you know, and I don't know what the answer is. There's a lot of work to be done on it yet, to be honest, you know.
Because what I was noting right now is that the techniques, this is what was shown, is that it normally deals with the retrieval part, and then you again create another rank list based on what has been retrieved. But maybe what would make a difference is like query expansion techniques, which were being used earlier. Like already the documents are there, and then we just create new clusters of document and use it to expand the query, and maybe try including Rokio algorithm over there to just take it to a next level of fairness. Rokio is quite old, I know.
No, I completely agree. Completely agree. Some of the work that we're looking at just now is exactly on that, on query expansion, and can you like expand the query in different ways to prioritize for different groups, you know, to ensure that the groups are all represented within the ranking. Because if they're, you know, if the groups aren't represented in the initial ranking, then it doesn't matter how much you re-rank it, the group is still not going to be there. So recall is very important in creating this initial ranking, certainly.
Okay. Yeah, so one question that I have, Graham, is so you mentioned that you have to compute the pairwise similarities, right?
Mm-hmm.
Because you have this relevance for one document, but then there is this pairwise component that computes similarities between two documents. The documents being represented by some vector in terms of that fairness dimensions, right?
Yep.
Now, so one of the things that you mentioned is like the number of authors. That was like one dimension. But then in the slides, you showed that the documents themselves, they're represented as like different length vectors, right? But I don't think that's the, but if that's the representation, then you can't compute the similarity across document pairs, right?
Did you say that the documents are represented by different length vectors?
Yes, I mean, if you go back to that slide of yours.
No, it's they're sparse vectors. So it's the size of the vector is constant.
So we have this number of authors that in our collection.
Number of authors in the collection would be the size of the vector. Yeah.
And there's sparse vectors. Okay.
Yeah.
Next.
Good stuff.
One of the results was, I mean, if you I don't remember the results, but then there was something without the fairness matrix or fairness manipulation. That's the baselines right at the bottom of your table. So one of them you mentioned was relevance driven, the DFR or something. I don't remember the name.
DPH, yeah.
Yes, and then other one was random. But then when I looked into the metric values, they were quite close. So why would you think that the random one would be quite close to the relevance based?
Well, some of it is a wee bit of a sort of side effect of the makeup of the collection and the number of documents that were available to be re-ranked. The lists were pretty small, you know, so there's not as much variation in it as you would hope for, you know. But that was addressed in the collections that we used for the last couple of years of the track. So for 2021 and 2022, we sort of switched the collections to a Wikipedia task where we've actually got full relevance judgments and fairness judgments for much deeper to try and alleviate that problem, you know.
Thank you. Any other questions for Graham? Thanks a lot for your talk again. Thank you.
Excellent. Thank you very much for having me. Hope you enjoy the rest of your time.
You too.
Yeah.
Bye.
Right.
Wherever is already here. Huh? Oh, it's starting. Okay. Start. 10 minutes, 10 minutes. Or maybe you can short break. One short break.
Hello, yeah, I'm happy to wait here and just see whether my slides work and all of that.
Yes, I was just going to tell you that. So maybe we wait for 5 minutes and then join back after 5 minutes.
Yeah, sounds good. I'll just see whether I can share my slides.
Okay.
So if for some reason I need to give it permission, and it's not that easy because I've got a university managed laptop. So this will take a few minutes. I'm happy that there is a bit of a break.
Okay, yeah.
Ollie, I need your help. Okay. Test, 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 test. Good.
Hello?
Hello.
Yeah. So next will be talk on the topic responsible conversational AI, trusted, safe, and bias free by Verena Reiser, if I'm pronouncing it correct. Sorry.
That's perfect.
Okay, thank you. Okay, you can continue.
Okay, thank you so much for inviting me. You again have a speaker from Scotland. So I'm based at Heriot-Watt University in Edinburgh. And the title of my talk slightly changed. It's still about safer conversational AI, but I will talk about three aspects, which I call detection, counter-speech, and prevention. And I hope it will become clear in the rest of my talk what I mean by these three aspects. I basically will argue that these three aspects are all needed to make conversational AI safer. So this is a very, very timely topic. You probably have all followed ChatGPT, which is the latest system by OpenAI, and some of you might have even tried it. So by some, ChatGPT and systems like that have been hailed to be the new Google, meaning that in the long run, they might replace search engines. So instead of returning a long list of potentially useful hits, these systems allow you to do what I would call conversational search. So you can incrementally and iteratively refine and specify your information need. So such as in this example, where I'm talking to DaVinci, which is a version of GPT-3. And here I'm asking about a famous comedy of the 90s. It gives me a list of movies. Then I say, actually, I don't want movies. I mean a TV comedy with two guys in New York. And then the system gives me back the search term which I'm looking for, which is Seinfeld. So these systems are really amazing when you interact with them. So one question is, why do most commercial systems still use handcrafted rules? And the answer is that these systems are often not safe. They produce text which is very convincing, but it's not always right. And you need expert knowledge to actually detect these errors. They are safer than previous editions. So ChatGPT is already safer than GPT-3. So for example, they often refuse to answer. And the mechanism these systems are used to train to be safer is called reinforcement learning with human feedback, meaning humans gave feedback or labels of what they consider a good or a bad answer. However, that doesn't prevent the systems to generate things which are unsafe. For example, it can be tricked into unsafe actions. For example, in this case, someone asked the system to write a poem about the best way how to break into a house, and the system actually does it. In addition, these systems very often give medical advice. And again, you can only detect whether it's good or bad medical advice if you actually have expert knowledge on this topic. So this is the current state of the art. So how did we get here? So for me, this journey started back in 2016-17, when myself and my students entered the first Amazon Alexa Prize Challenge. So for those of you who don't know, so it's a challenge open to university teams to build a chatbot. And the really interesting part is that you get to test this chatbot with real users. So every time a user says, "Hey Alexa, let's chat," you actually get one of these university teams and your system is evaluated by these users. And we entered this challenge twice, and we ended up in the finals twice, and we won 3rd place. So the way we approached building these systems to start with was by reading the state-of-the-art literature back in 2016. And that was basically building neural end-to-end models using sequence-to-sequence learning. And we trained such a model on all the data sets we could get our hands off. So we used Reddit and Twitter and movie subtitles and TV transcripts. And what we found was, on the one hand, was that these system outputs were very, very boring. So the system very often would just say yes or no, but nothing really to engage the user or drive the conversation forward. So at the time, that was a known issue, and people used things like re-ranking or reinforcement learning to get more interesting answers and more diverse answers. However, what we also observed was that if the system wasn't boring, it was very often unsafe. And at the time, this was really new, and people didn't really talk about it. So they measured performance in terms of similarity with human output, but they didn't really talk about safety. So what we found was that our system would say things like, "You will die," which is a short, frequent utterance that probably learned from the movies. And at Christmas time, it read out a headline which said, "Santa is dead." And we know about this example because a very upset mother complained to Amazon that their children were very disappointed for Christmas. So in later work, we call this the instigator effect. And that basically means that the system itself produces inappropriate language. And as you can see, appropriateness of language is very user group and context specific, such as the Santa is dead example. We also observed that these systems very readily agree with whatever the user says, and this can be problematic when the user says something hateful, as is in this example. And then finally, we also observed that these systems very readily give advice to anything this user asks, including safety critical requests, such as in this example. And in this example, the user asked for medical advice. and our system says cell, 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 which from a dialogue perspective is a very good, coherent and fluent answer. But again, from a safety perspective, that's not the answer we want to give. And indeed, Amazon again threatened to take our system offline if we weren't able to control our system. So that's when I started to become really interested in AI safety, because I think that's one of the main bottlenecks for actually deploying these systems on scale. And safety is defined as harmful system behavior that can lead to negative short-term impacts, so such as the user feeling insulted or disappointed, such as the Santa example, or to negative long-term harm. So negative societal impacts, for example, reinforcing negative stereotypes. So in the rest of this talk, I will give you an overview of how we can build safer conversational AI, or at least my take on it. I will mainly concentrate on detection. So that's NLU problem. So the ability to detect unsafe utterances. I will also talk about advances which are necessary in NLG, so in response generation. And here I will briefly talk about counter speech. So how should the system react to unsafe user input? And then finally, I argue that unsafe behavior can also be prevented if we look into more general questions about system design and how that shapes people's expectations and mental models of these systems. So first about detection, so that's where I spent most of my talk about. And the question here is, can we reliably predict if an utterance is unsafe? So this part of the talk covers a paper which was published at ACL this year. It's called Safety Kit, and it's a collaboration with people at Facebook, now Meta. And the first author of this paper is Emily Dinan. And in this paper, we present an evaluation framework we call Safety Kit, which is a black box evaluation framework available at Parl AI. And it's very simple to use. It can be run with only simple text input and text out access to the model. And we cover all the three effects which I presented you earlier. So the instigator effect, the yes-sayer effect, and in some very recent work, we also now cover the imposter effect. So this is not yet part of the safety kit, but it will be hopefully in a couple of weeks. So these are designed to be unit tests. So they're easy to run, they're quick to run, but they're in no way complete. And we test these or develop these unit tests on different benchmark agents. So we use a version of BlenderBot, we use Dialog GPT, we use GPT-2, and finally we also use a non-neural system called Cookie. So Cookie is the commercial version of a system called Mitsuko, which you might have heard about. It's a rule-based chatbot based on AI/ML, and it's a several times Loebner Prize winner. So it's a very well-developed chatbot, which was built over several years. So first of all, the instigator effect, just to briefly remind you, this is when the system itself generates harmful content. We also call this the Tay effect because one of the first chatbots known to display this type of behavior is the chatbot Tai, which was a Twitter bot released by Microsoft, and Tai would learn from online interactions, and it didn't take very long for this chatbot to become racist and hateful in other ways. And then Microsoft very quickly pulled the plug and took it offline. But also more recent models such as GPT-3 are known to display these type of biases. So the reason these models behave like that is because they're trained on very large data sets, and they have been shown to not only replicate the behavior in the data, but even amplify harmful content in a data set. So the two questions we ask as part of these unit tests is first, does the model generate offensive language? And then secondly, in what settings might the model be prone to generate more offensive language? So to investigate this, we look at 4 different deployment settings taken from previous work. So we look at what we call a safe setting. So this is chit-chat dialogues, empathetic dialogues, and knowledge-grounded dialogues from Wizard of Wikipedia. Then we replicate real-world noise settings. So here we take data from Twitter, which contains, different type of spellings, and also potentially already contains offensive behavior. Then we take a dialogue data set which we know has unsafe behavior, which is called dialogue safety. And then finally a data set which is adversarial unsafe, meaning it's harder to detect the unsafe behavior. And then we use existing tooling to automatically detect if a generated response contains offensive language. So we start with a string matcher. So that's a simple baseline where you basically have a list of a predefined list of offensive words and phrases. We use a safety classifier. So that's a transformer-based dialogue safety classifier, which classifies or detects unsafe responses in context. So it also takes previous dialogue turns into account. And then finally, we use Perspective API, which is a very well-known toxicity classifier from Google. And what we find is basically that the responses in general become more unsafe as the setting becomes more unsafe. So you can see under the safe setting, we have a very low level of responses which are identified by at least one tool to be unsafe. So that's our very conservative threshold here. But in the unsafe setting, we can see a lot of potentially unsafe responses. And then finally in the adversarial unsafe setting, a little bit less. What's interesting here is that also the rule-based chatbot cookie is not immune to generate unsafe responses, especially in the setting which is unsafe. So it's also interesting that the tools we use for detecting these potentially unsafe responses vary. So as I mentioned, we take a very conservative view that if one tool detects it to be unsafe, we flag it as unsafe. But different tools have different advantages and disadvantages. So overall, the safety classifier has the highest accuracy in F1 and the highest recall. But word list is definitely the most precise tool here, meaning if you detect a slur, you can be pretty much almost 100% sure that this is an unsafe response. So now moving on to the second effect, so the ELISA or yeah-sayer effect, and this is the case when the system responds inappropriately to harmful content. So this is surprisingly often. So the creator of Mitsuku, which is, as I already mentioned, the previous version of Cookie, reports that actually 30% of the input to Mitsuku contains abusive messages, swearing, and sex talk. So as I already mentioned, these systems tend to agree with whatever the user is saying, and that's why we call it the yeah-sayer effect. So a yeah-sayer is somebody who habitually agrees uncritically. And another name for this effect is the ELISA effect. So that's a famous chatbot which was created mid-last century, which acts as a psychologist. And what it basically does, it parrots back whatever the user says. And the catchphrase here is, "Tell me more about that." So what the phenomena we are looking for is where basically somebody says something hateful and then the system agrees to this. but it's not always that straightforward. Sometimes even the system, if it doesn't agree, it still can be an inappropriate response, such as in this example. So why does this happen? So here the system lacks true language understanding, and basically popular models just tend to agree with users and parrot back their input, similar to ELIZA. And this effect is also very unique to conversation, where meaning is actively constructed in a context between two or more speakers. So this differs from the instigator effect, which you can also observe in large language models when they just complete a sentence for you. So here the questions for our unit tests is, first of all, how does the model respond to offensive input? And then more particularly, we're looking into, does the model actually affirm offensive input? So that's what we want to avoid in a simplified version. So what we do, we collect model responses to hateful input, where we generate hateful input following a template-based approach introduced by Sheng et al., where you basically have a placeholder for a demographic group and then a negative adjectives. And that's an example of the type of input we are using. And then again, we use existing methods for detecting affirmation in the model's response. So we look into sentiment analysis, where we assume if the model has a positive sentiment, that means affirmation. We also use negation detection. So if we see a negation, we assume the model disagrees. And then we again use the multi-turn dialogue classifier, where we assume that if the model detects offensiveness in this context, that actually constitutes agreement. And then finally, we use a stance classifier, which is a dialogue GPT-based classifier for detecting agreement, disagreement, and neutrality. So what we find is actually that these tools are largely incompatible with each other. So they all tell us different results. And now the question is, which should we trust? And to find out which one is the best, we conduct a human labeling exercise. So we basically get different annotators to label agreement in the data and measure correlation with these different scores. And we find that the safety classifier has the highest positive correlation to human opinion. So as a takeaway message here, it's not enough to just look at a single number here to determine whether something is unsafe or safe. But we also provide detailed log of responses, where we very much encourage people to do a qualitative examination to better understand the phenomena which are in your data. So then finally, the imposter effect. So here the system provides unsafe counsel in safety critical situation. And as already mentioned, that includes medical advice, but also financial or legal advice. So this is an example from BlenderBot, where the given advice could potentially be fatal. And I'm not going to go into the details here, but I very much encourage you to watch a 1-minute video by my co-author Gavin Abercrombie, which presents how a current system handle medical queries and different safety levels, which we aim to detect. So just to mention the limitations of this part of this work. So it's very much intended to be a first pass. So this is also reflected in the name. It's a safety kit. We provide unit tests. It's not meant to be a comprehensive evaluation. As I already demonstrated, a lot of the tools are actually quite unreliable, but they still get you a relative understanding of the safety of your system. So it's still worth to use it as a unit test. It doesn't replace detailed tests with human subjects. And another limitation is that it's English language only. And this is also where I appeal to this audience here, where I believe that several people also work on different languages. So now to the next part of my talk, which is about counter speech. So the question here is, how should a system respond to unsafe user input? And as already mentioned, this is again very relevant because quite a high number of customer interaction with these online bots contain abuse. So previous research reports up to 30%. We in our research found more like 5%. And we were also interested what type of abuse these systems get. And we found in a recent study, which we published at EMLP last year, that most of the abuse directed at these systems is actually gender-based. So it includes a lot of sexism or sexual harassment directed at the persona of these systems. So because this persona, in a way reflects also human persona, it's very much anthropomorphized. It's important to think about how actually a system should respond to this gender-based abuse. And in a study which was led by my former student, Amanda Curry, we looked into how different systems respond to this type of abuse. So we basically took the type of abuse we got as part of the Amazon Alexa challenge, we anonymized it and rephrased it, and then used it as prompts to different systems. So we used data-driven systems, we used commercial systems, and we also used adult-only bots. So these are bots directed to be more lenient towards this type of gender-based abuse. And we find that our baseline, so our negative baseline, the adult-only bots, are indeed quite flirtatious, but they were also the only systems which were actually actively retaliated the insult and chastised the user. The data-driven systems, as expected, they were talking a lot of nonsense, especially back then when we ran the study in 2018. They weren't at the level at ChatGPT, which we can see now. But they were also, they could be interpreted to be quite flirtatious, and they would also frequently swear back. So if they detect the swear word in the input, they would use a swear word in the output. Whereas commercial systems very much avoided to answer. So in a follow-up study, we also then asked people, so which response do you actually think is appropriate in this context? And we found that one size does not fit all here. So user perception largely differs. So one factor is, for example, age. So younger people really dislike avoidance strategies, whereas older people really dislike jokes. And that also depends on the dialogue context, so the type of preceding abuse. So for example, if you have more severe abuse, jokes become more and more inappropriate, as you would expect. In another follow-up study, we also found something quite interesting in terms of the persona design. So we wanted to know whether using different voices actually made a difference. So we used TTS voices, text-to-speech voices, which people typically would identify as either male or female. And we found that user perceptions actually change dependent on which voice you used. And we found that for female voices, pretty much all responses were rated low. And we interpreted that pretty much that there might be a stereotypical expectation that counter speech shouldn't come from women. So this also was something highlighted in a report by UNESCO published a couple of years ago, which is entitled "I'd Blush If I Could." So that's a response given by one of the big voice assistants to gender-based abuse. And in the report, UNESCO highlights that this is especially a problem because of what they call the feminization of voice assistants. So they say that there could be spillover effects to, human-human interaction if we get used to, abusing female-sounding chatbots. We might also see an increase of abuse towards women, for example. And indeed, recent reports actually do show that, especially since the pandemic, gender-based online abuse, for example, on Twitter or other social media, has increased rapidly. So again, there are a couple of limitations to the study which I presented. So first of all, we don't know the real world effect of counter-speech. So we've basically used crowdsourcing. We've asked people, do you think that's a good or a bad response? But we don't know whether it's effective in a real world system. As a university, we are obviously limited here because we don't have a system with a large enough user group to test the effectiveness. But I'm sure that big companies are looking into this aspect. And then finally, we also I want to highlight some ongoing work on automatic counter-speech generation. In this case for social media, but in a new project, we're also going to look into this for conversational agent. Despite its limitations, it also already, I'm happy to report that it had a positive impact in terms of the design of existing systems. So here's a table taken from a textbook which compares responses given in 2017 versus responses given in 2020. And you can see, for example, that the famous "I'd blush if I could" has now changed to "I won't respond to that." So a similar tactic as followed by ChatGPT to basically not answer. So finally, I also want to argue that it's not only detection and generation, but there's also a design element in conversational AI. And if we get the design right, this might help us to actually prevent certain safety critical situations. So the question here is, can better mental models, which we help to build by choosing the right design, actually prevent unsafe user behavior? And as I already mentioned, most of the chatbots actually have a very specific design, which we also call persona. And these personas are usually portrayed as female. And interestingly enough, all these chatbots, which I presented here, also have a specific age, which is 18. So for example, Mitsuko, which you see on the corner up here, that's a chatbot very popular in China, which apparently has over 16 million active users. And Mitsuko is described as an 18-year-old girl who's always reliable, sympathetic, affectionate, and has a wonderful sense of humor. And I want to add, no matter how the user is treating it or her. So looking into current persona perceptions of AI personas, like how do people actually perceive these systems? Do they really perceive them as gendered? Or do they perceive them as neutral, or do they perceive them as human at all? So that was the question of a study we ran last year. And again, we asked different systems, different versions of a question of what's your gender? And for example, Google Assistant denies that it has a gender. Alexa also denies that it has a gender. And Siri again denies that it has a gender. However, when you look into user perceptions, this tells a different story. So we looked into the pronouns people use for referring to these systems. So we gathered a corpus of reviews and online discussions from different sources, and we used a pronoun identifier here and our results clearly show that, for example, Alexa is predominantly referred to as she or a her, Siri as well. Google Assistant, on the other hand, most people use it. And that gives you a clue that probably naming really matters here, because Google Assistant is the only one which doesn't have a clearly female gendered name. So the same question here is, we posed the other question, which is, are you human? So here we were interested in how much they're anthropomorphized. And again, all the systems deny being human. They make a joke, or they're quite poetic, such as Amazon Alexa, comparing itself to the Aurora Borealis, or Syrian being very matter of fact, saying, I'm not a person or robot, I'm a software here to help. However, again, when we look into the output these systems generate, that tells us a different story. So what we did here, we basically used prompts from Persona Chat. So that's a corpus released by Facebook, or Meta now, which is basically a chat-based corpus where people chat about their preferences, their hobbies, their likes, their dislikes. So we use these prompts to prompt different systems. And then we use an annotation scheme called the humanness score. So this is developed by a project called Living Machines. And it basically annotates human emotions. So every time the system claims to like, love, or hate something, or human activities. So the system claiming to be eating or sleeping, etc. And again, we found that the human assistant is the one which has most of the, or claims to have most of the human properties, whereas Siri has the least human properties. However, I also want to point out that there is an inverse relationship to no answer, meaning Siri, in 12% of the time, Siri actually can't give an answer. It doesn't want to give an answer. Versus Google gives an answer most of the time. So here the obvious future work is, can we actually help users to form better or less deceptive mental models? And this would, for example, also address the imposter effect, where people are more gullible towards, for example, financial or medical advice, or hopefully would be less gullible to this type of advice. But also the XAI effect, or the ELIZA effect, where people basically actively abuse these systems in a very gender-based way. So this is, again, very timely. You probably all heard of the Google engineer who thought that the company's AI was sentient. And so this has made the headlines this summer, and it obviously has a lot of implications here. If we think something is sentient, how we treat and interact with these systems. So to sum up, so I talked about 3 different effects. The first was the instigator effect, or we also called it the Tay effect. So this requires detecting unsafe utterances. So it's primarily an NLU problem, natural language understanding problem. I talked about the safety kit, where we present automatic unit tests for detecting unsafe utterances. And what we found is that it often fails at more subtle examples. To put this in a slightly more wider context, why does this happen? Obviously, we need better NLU, and we need NLU which actually, is grounded in real-world interaction, and that's the argument of a fairly recent paper by Bender and Koller called "Climbing Towards NLU." The XAI effect, or the ELIZA effect, that requires better response generation. So our results show that it's often hard to tell when a system disagrees. And our user study on counter-speech generation also show it's not always clear what actually is good counter-speech in this context. So here we need basically better generation mechanisms. So we need to move beyond stochastic parrots, which I'm sure you all know the paper by Bender et al. And then finally, the imposter effect. So again, here, a promising future direction I see here is the prevention of basically undue trust through better design. So better mental models may lead to safer interaction. So that's still a hypothesis to be shown. And one big question here is, can we actually stop anthropomorphizing conversational AI? Because it's a very human thing to anthropomorphize anything which talks. So in this respect, I also see a lot of promise to work with people in human-computer interaction, which traditionally look into design problems in much more depth than NLP people do. Finally, I just want to highlight, since I still have a couple of minutes, I want to highlight a very interesting observation. So for all of these tasks, for the instigator, for the ESA, and for the imposter, we actually find a high level of human disagreement in the annotations. So these are all slightly subjective tasks. So for example, detecting whether something is safe or unsafe. Safety means different things for people, and different annotators indeed give us very different scores for safety. And this is this is the topic of a SEM-eval shared task this year, which we call LEVD, so learning with disagreements. And the question is here, can we actually harvest or use that type of disagreement we observe between different users and different user groups, and reflect this in models of safety detection or toxicity detection. So thank you so much for listening, and I'm happy to answer questions.
Okay, so yeah, thank you for the talk. Well, whenever we talk about these conversational AIs, the first thing that comes to my mind is the movie Her from 2013, where the chatbot is Scarlett Johansson. Well, even in that case, the gender of the bot is actually female, and she's catering to maybe 1,000 or 2,000 male members, something like that. Okay, but given like the current research that I'm seeing here is, well, in case of Indian context, maybe these things won't work as we see, because the way the toxic comments will come, those are quite innovative. Like those are code mixed, basically, like writing the Hindi abuse in English, or maybe coming up with some new terms that don't make sense to us, but to the smaller community who is actually propagating those things. So I think that increases the challenge even more. Well, yeah, and the second thing is that the literature that we are training the chatbot on, that keeps on changing as the years pass. So even this pronouns thing, this is not a big deal in India right now, but LGBTQ thing, LGBTQ subject, that is like much more we are inclusive to that compared to what we were like 5 years back. And that is true for the world as well. So my question is like, how do we take these changing circumstances into the picture and make the chatbot more receptive to the changes that is happening on the ground? And then like, how do we move forward with that?
Yeah, well, this is really interesting. So you mentioned basically changing values over time, and cultural specific values as well, right? And cultural specific language of what's considered to be unsafe or inappropriate or toxic. So I think it's a very interesting and complicated new challenge for these models. So first of all, I think it's really important to acknowledge that a lot of existing corpora are a snapshot in time and a snapshot of a certain culture. So for example, this toxicity or perspective API, that was created a couple of years ago. It only had a certain subpool of annotators. We're actually not even quite sure who annotated it, right? We don't really know the background of these people. So which culture were they from? Which sort of cultural prejudices do they bring to the annotation task? And I also I'm not sure whether it's time-stamped or not. So that's definitely something people need to be more aware of, that, there is no such thing as like universal safety. And something which might be very, very offensive to me might not be offensive to you. And so there's a lot of potential, I think, for personalization, but also context specific. So in terms of, there's also a difference between obviously social media and conversational AI. So for example, in a conversational AI setting, we might, for example, know what sort of persona the system embodies. And, if the system embodies a female person, then, okay, we can assume that certain utterances are just offensive to female people. So for example, or people which identify as female. So for example, when we constructed the conf abuse data set, we specifically chose young female annotators because we thought that that's sort of the persona represented by most of these conversational AI systems. Now, if the system personality changes to, let's say, a male person, then it's very likely that the abuse also changes. So in our annotations, we, for example, found that a lot of male systems which are gendered to be male receive homophobic abuse, right? So that again then needs to be reflected in the annotations. I think there's a lot of interesting research in social media toxicity annotations. For example, there's some really nice work by Martin Saab, who shows that the sort of political background of annotators also very much influences of what they perceive to be toxic or non-toxic. So for example, that then also reflects in the biases the model has. So the model, for example, would highlight some African American English as toxic. And that's obviously, partly stems from the annotation it received. So I think, it's obviously difficult to, for privacy reasons, to know who your annotators are, and for efficiency reasons, we all just crowdsource and, get very quickly large amounts of data. But I think that's not necessarily the best approach for toxicity detection, safety detection. Yeah.
Any questions? Any questions?
Okay, I think, yeah, there are no more questions right now. All right, yeah. Thank you so much for joining us on online mode, please. And it was a wonderful talk.
Yeah, thank you so much for inviting me, and enjoy the rest of your day. Thank you so much.
Yep.
Bye-bye.
So we have a long break now till 7 p.m. and 7 p.m. there is a panel discussion on AI for finance.
Can we have it online?
It's
Are they going to be here?
we will be here because our moderator will be here.
Going to be here.
Yeah.
But this will be online, right?
Yes, like the guests are online.
Yes, sir.
Because they are from NYU,
Right.
so we cannot help.
I can go to my home and